राठौर सर,
हाँ,
नॉइस है बहुत।
वॉइस मैडम के मैडम के इसका
मैं बंद करती हूँ, फैन बंद करती हूँ।
नहीं मैम, वो एक्चुअली क्योंकि उधर कुछ बोलेंगे ना तो स्लाइड चेंज करते वक्त फिर मुझे आवाज नहीं आएगी बराबर से।
Yeah. Now switch off the fan. Now see. Is it still there?
No, it's fine now.
Now it's fine ना, तो फैन का नॉइज है।
Yes.
Let's switch it off.
Okay मैम, थैंक यू।
वेलकम।
अभिषेक,
अरे ये किधर से मुर्गा बोला?
वो मुर्गा स्नेहा मैडम का मुर्गा है, वो
हाँ
सेट कर रखा है, जब भी टाइम होगा तो मुर्गा कुकड़ू बोलता है।
हाँ, मुर्गा बोलता है एकदम से।
और हमने आर्टिफिशियल मुर्गा रखा है, रियल मुर्गा रखा है।
अरे वाह, वेरी गुड।
मेरे को लगा तुमने मेरे को मुर्गा बोला है।
सर मैं वापस आते वक्त सबके लिए लेके आऊंगी एक एक।
अरे वाह, क्या बात है।
हम लोग वेजिटेरियन है,
तो वेजिटेरियन मुर्गा लेके आऊंगी मैम।
वेजिटेरियन मुर्गा भी होता है स्नेहा।
पता है मैम, कुछ और लेके आ जाऊंगी आपके लिए।
Where are you? You are at Bombay or you are at your hometown?
होम टाउन मैम।
Which place?
इट्स इन गढ़चिरौली डिस्ट्रिक्ट मैम।
महाराष्ट्र ओनली ना?
या महाराष्ट्र ओनली।
अभिषेक,
अभी मैं थोड़ी देर फैन ऑन कर लेती हूँ।
हाँ,
When we start,
जब आपका ये आएगा ना मैडम,
हाँ, तब मैं ऑफ कर। नहीं, when we start also I will switch it off.
ओके। मैं एक काम करता हूँ, वीडियोस ऑन करता हूँ, अभी अपने पास 5-10 मिनट है ना, अपने कॉलेज के वीडियोस ऑन करता हूँ। तो स्नेहा मैडम, आई विल रिमूव योर शेयरिंग, आई विल स्विच ऑन टू सम वीडियोस, ओके, बिकॉज़ वी हैव 5-10 मिनट्स।
मैं स्टॉप करा, अदरवाइज ते पुन्हा हँग होतो।
हाँ,
you're screaming out, you can't make a sound, you know it's only a dream. When you're back and things turn around, you know it was only a dream. 'Cause nothing is as bad as nothing. When you're pulling at the seams, when the lights go, you still got me. Oh,
Good morning to all of you. Dr. Abhishek, are you there? Shall we start?
Yes, I am ready.
Yeah, okay. So we'll go ahead. Priya ma'am, go ahead.
Very good morning to everyone present here. Respected Chief Guest Dr. Abhishek Sharma.
Priya ma'am, your voice is breaking.
Hello. I'm audible.
थोड़ा और अच्छे से. Breaking.
I'm audible, sir? Hello.
Yeah. It's very clear now. Go ahead.
Oh, okay. Due to technical issue, sorry. A very good morning to everyone present here. Respected Chief Guest Dr. Abhishek Sharma, Intel Corporation USA. Dr. B.N. Chaudhary, Principal of our Institute. Dr. Rita Das, Dean Student Affairs of our Institute. Program Evaluation Committee members, Dr. D.C. Karya, Head of Electronics Engineering Department. Dr. Rita Sonkusre, Head of Electronics and Telecommunication Engineering Department. Dr. Kanya Kulkarni, Associate Professor at Electronics and Telecommunication Department. All Deans and HODs, dear colleagues and all the participants. I, Priya Deshpande, on behalf of Sardar Patel Institute of Technology, welcome you all for the inauguration ceremony of AICT sponsored 1-week online STTP on VLSI design using cadence tools, mixed signal VLSI design. After successful completion of 2 STTPs in the domain of VLSI, the topic of digital CMOS VLSI design and analog CMOS VLSI design, we are stepping towards our third STTP now. The theme of mixed signal VLSI design, scheduled from 30th November to 5th December 2020. We always start occasion with a Ganesh Vandana. Let's grace this occasion with a small prayer. Vakratunda Mahakaya Suryakoti Samaprabha Nirvignam Kurme Deva Sarvakayeshu Sarvada. Gurur Brahma, Gurur Vishnu, Gurur Devo Maheshwara, Gurur Sakshat Parabrahma, Tasmai Shri Gurave Namah. It's a very blissful day on occasion of Guru Nanak Jayanti. We are inaugurating our STTP3. So let's pray for the God. Now I request the coordinator of a STTP, Dr. Surendra Rathod, to give an introduction to our program. Over to you, sir.
Yeah. So good morning, one and all. Good morning to our today's guest of honor, Dr. Abhishek Sharma. Good morning to our principal sir, Dr. B.N. Chaudhary. Good morning to our Dean Students Affair ma'am, Dr. Rita Das. Thank you very much for joining, ma'am. Good morning to all the participants. Good morning to PEC members, Dr. Reena Sonkusre and Dr. Sukanya Kulkarni, ma'am. Thank you very much, ma'am, for joining this today morning. So I welcome you all for this third STTP on VLSI design using cadence tool. You all aware that we had 3 STTP programs in VLSI domain. First one was covering digital technologies, which we have already successfully completed. Second was on analog CMOS technologies, that also we have completed. So now obviously we have a combination of these two, mixed signal VLSI design. And this workshop probably is a very challenging workshop in terms of technology, in terms of even getting the resource persons who are going to talk on mixed signal concepts. And we are fortunate to have very good resource persons for this workshop as well. So now shortly we will be starting with our very own Dr. Abhishek Sharma. I'll shortly introduce him. Then after his speech, today's morning session will be conducted by none other than Dr. Maryam Baghini ma'am from IIT Bombay. I'm really thankful to her for accepting the invitation as a keynote speech and accepting to deliver the complete spectrum of mixed signal design in the first 1.5 hour, and then talking about the basic principles of switch capacitor circuits. So we'll be fortunate to have day one starting with Dr. Abhishek Sharma and Dr. Maryam ma'am. Then at the evening time today, we will have Dr. Ramesh Vaddi, who is from SRM University. Then second day will be kind of a demonstration sessions from Entupal Technologies, who are third party vendors for the cadence. So they will be demonstrating various tool sets on full custom and semi-custom IC design. They'll be demonstrating on synthesis and pre-layout static timing analysis on day one. Then they will go ahead with the physical design verification flow. They are going to cover floor plan, power plan, APR, clock tree synthesis, and entire physical verification design flow. They will also demonstrate you about the placement routing of system on chip using their tool set called as Innovus. So basically, on 1st and 2nd December, you are going to have a lot of demonstrations on cadence. But I have also arranged one evening talk on the same day, that is 2nd December, by Dr. Prashant Nair. He is from the University of British Columbia, and this is the time period which we were able to match, and therefore it has been scheduled on 2nd December. So participants, be ready for 2nd December, because 2nd December you will be full packed from morning to evening. Then on 3rd December, we will have a session by Dr. S. Kumarvel. He is from VIT Vellore. He will be covering data converters. So basic principles of data converters like ADCs, DACs, their architectures, etc. On the same day, in the evening slot, we will have Mr. Miraj Ahmed. He's a research scholar at IIT Bombay, and he's working from last 7 years on mixed signal domain, in the mixed signal domain. So he will be demonstrating you about dynamic offset cancellation techniques. And then on 4th, we will have Dr. Mohammad Hassan from Aligarh Muslim University. He will be taking your session on low power architectures for signal processing and communication. And then in the evening slot, we will have a case study, and you can say, you know Dr. Shaila Subbaraman ma'am, and we are fortunate to have her back in this activity as well. So evening slots, we will be talking about implementation of DSP algorithms in VLSI. And finally, we will end our session or this STTP or series of STTP, you can say, in the VLSI domain on 5th December with well-known Dr. Jagbir Singh, who is going to take us to a mind power session, a 1 hour exciting session on the 5th December. So this is what is our plan for this entire 1 week STTP on VLSI design using cadence tools, particularly mixed signal VLSI design. So I wholeheartedly welcome all of you for this third STTP. And as usual, we will have assessments. Every day there will be a quiz. So tomorrow morning, quiz will be scheduled from 8 a.m. to 10 a.m. In between this 8 a.m. to 10 a.m., you have to compulsorily appear for the quiz. For 30 minutes, quiz will be there. So there will be continuous assessment carried out on each and every day, and there will be final quiz on the last day. So as per IICT, all of you know that it is compulsory to have evaluation committee. It is compulsory to have a PEC, that is called as Program Evaluation Committee. So I'm thankful to Dr. Reena Sonkusne ma'am, Dr. Sukanya Kulkarni madam for providing their help and be part of the Program Evaluation Committee. And as a guideline of Program Evaluation Committee and AICT guidelines, all of you have to appear for these assessments, and you must get 60% marks, apart from regular attendance for these courses. So I welcome you for this exciting journey, and hope you will like all the sessions and all the assessments also. And please interact during all the sessions. That's my sincere request to all the participants. So thank you very much. Over to you, ma'am. Yeah, ma'am.
Thank you, sir, for taking a tour to a proposed full-fledged package of STTP and giving an overview of session and speaker of STTP. Okay, Maryam, STTP.
Yes, yes.
Noise is, yes.
Madam, background noise.
Okay. I'm happy to share with you all that we have expertise. Okay, I'm happy to share with you all that we have expertise in the field of semiconductor as our very own faculty, Rita Das.
Yeah,
Should I wait?
Priya
His
madam,
noise is coming.
just a minute. Priya madam, just a minute, just a minute. Rita Das madam, your fan is on.
Off, sir. Off. गर्मी में बैठी हूँ. Off है. Off है.
Now it is okay. Now proper. Okay. Go ahead. Priya madam, go ahead.
Okay. So we have very own faculty, Rita Das. Dr. Rita Das is Dean Student Affairs of our institute, and she's heading the Department of Applied Science and Humanities. She has completed her PhD from IIT Kanpur in social physics. This is the best opportunity to speak to her along with us today. I welcome you, ma'am. Request you to share your thoughts.
Thank you. Thank you, Priya. Our keynote speaker for today, Dr. Abhishek Sharma, Dr. Maryam, Dr. Surendra Rathod, coordinator of STTP, the members of the organizing committee, my dear colleagues and dear participants. Very good morning to you all. It gives me a great pleasure to welcome you all this morning at the inauguration ceremony of AICT sponsored 1-week short-term training program on VLSI design using Tedesson tools. Mixed signal VLSI design, which is the third program of the series. I'm extremely happy to be a part of this inauguration ceremony, and I take this opportunity to thank Dr. Rathod for inviting me today. I feel very proud as a faculty of S.P.I.T. and our own alumni, Dr. Abhishek Sharma, is one of the keynote speakers today. We all have been going through difficult times and facing new challenges every day in this pandemic situation. But the brighter side of this is that we have got an opportunity to upgrade our skills and knowledge in various domains through online AICT, STTP, and ATAL courses. My heartfelt thanks to AICT for giving this opportunity to all of us. These courses are equivalent to 2 or 3 credit courses with evaluation through tests, quiz, and assignments. Some of these courses have hands-on session to improve practical skills, good exposure to the tool sets used by the industry. Organizing these courses are equally challenging as it requires a lot of coordination and effort. I congratulate Dr. S.S. Rathod, coordinator of STTP, and the organizing team for successful completion of the first 2 courses of this series. This is the third one. The first 2 STTPs were very well organized and well received by the participants. Selection of the speaker was thoughtfully done. Best part of these STTPs were its inaugural and valedictory session. As our own alumni were the keynote speakers at inauguration ceremony of these programs. It was wonderful experience to listen to them. It's a good platform to get connected with our alumni as it develops a bonding with them. We get to know their achievement. For valedictory function, the renowned personalities were invited to give a talk on the relevant issues relating to the current scenario. This also received a very good feedback by the audience. VLSI is an interdisciplinary science of utilizing advanced semiconductor technology to create various functions of the computer system. VLSI has revolutionized and has a wide range of applications in electronic industry. VLSI circuits are used everywhere. So this is a very, very relevant topic for STTP. VLSI design has achieved tremendous growth in worldwide markets since last few decades. There is a significant gap between the actual requirements of industry and the knowledge imparted in academics on the industry-grade tool sets. The main objective of this course or this training is to provide information through demonstrations of digital and analog blocks Through this STTP, we aim to give information which is necessary to effectively accomplish design of VLSI systems. This STTP also aims to share the experiences of professionals working in the domain of VLSI design. I would like to take this opportunity to express my sincere thanks to our honored guest, Dr. Abhishek Sharma, for sparing his valuable time for the session. I wish all the best to Dr. Rathod and the organizing team for the smooth conduction of this STTP. I am confident that all the participants will enjoy this course and gain expertise in the domain of VLSI. Happy learning week ahead to you all. Thank you.
Thank you, madam, for giving a overview of the course and giving the importance of the VLSI. And thank you for giving the best wishes for the course. Thank you very much.
Thank you, Priya. Thank you so much. Thank you, everyone.
So, as per the AICTE guidelines, we have formed a program evaluation committee. Yeah. The committee members are Dr. B.N. Chaudhary, Principal of our Institute as Chairperson, Dr. Deepak Karia, Head of Electronics Engineering Department, Dr. Reena Sonkusre, Head of Electronics and Telecommunication Department, Dr. Sukanya Kulkarni, Associate Professor at Electronics and Telecommunication Engineering Department as subject expert. So I welcome all the members of Program Evaluation Committee. Welcome, sir. Welcome, ma'am. Now I request our coordinator, Dr. S.S. Rathod, to welcome and introduce our keynote speaker and chief guest of the day. Over to you, sir.
Yes. So good morning once again, and I'm to invite and introduce our today's guest of honor, Dr. Abhishek Sharma. Dr. Abhishek Sharma is working at Intel Corporation at Component Research Group, Oregon, USA, and joining our program when there is a morning in India. Obviously, there is a night in the USA, and we are very, very fortunate that as soon as I send an email to our students, they immediately accept our request and revert back that yes, we are on. Thank you, Dr. Abhishek Sharma. So that means all of you participants might have realized that he's our very own student of S.P.I.T. Electronics Department. So Dr. Abhishek Sharma did his engineering from S.P.I.T. Then he completed his MS and PhD from Carnegie Mellon University in 2012 and 2015 respectively. His thesis was centered around using new memory technologies for high bandwidth applications. He is currently engaged in memory research at Component Research Intel USA. His core research areas include co-optimization of device and design in memory arrays for high performance applications. His core strengths are based on the strong foundations and 9+ years of experience in novel transistor research and in cross-disciplinary device circuit design interactions with a special focus on using new technologies to enable high bandwidth connectivity for tightly connected computer memory products. So as far as my knowledge goes, he is currently working on in-memory computing kind of architectures. So I'm really proud to say that our students have achieved greater heights in their life, and I'm more proud to see when they are working in the domain related to the courses which I teach them. So I'm very proud to welcome Dr. Abhishek Sharma for this session and looking forward for your speech for next 30 minutes. So Abhishek Sharma sir, thank you very much for accepting the invitation, and over to you.
Thank you very much, sir, and thank you very much, everyone, for the wonderful welcome. It is really an honor for me to present some tidbits of my acquired knowledge in front of such great personalities. So let me go ahead and present my screen. Please let me know when you can see my screen.
We can see, sir.
Thank you. Okay. So I collected a few foils based on some of the learnings that I've gained over the course of past several years regarding the memory design area. And while I do understand that this course is related to analog mixed signal design, you will find that analog mixed signal design finds its uses in variety of components that are used in the VLSI domain. Today I'll talk specifically on memory design. So I'll start off with the memory hierarchy, the memory pyramid, and I'm sure that a lot of you guys have seen this. With this pyramid represents the register files at the very top. Register files imply what we use as SRAM, and the storage which you see at the bottom is what we refer to as hard disk drives. In between them, we have 3D crosspoint that Intel produces, DRAM, and then SRAM. Now, the difference between these different memories is that the capacities used and just a moment, the capacities used and the access latencies of each of these memories is different. And as you might have seen earlier in textbooks, it is common knowledge that we need this memory hierarchy so that enough data is available, and that too at the right rate, so that it can service our compute needs. I'm sure I just heard that Prashant is going to give a talk later in this STTP, and I think you will certainly benefit a lot of architectural understanding in this area from him as well. So, so in this case, just to give some numbers so that people can remember and keep that in the back of their minds. Register files are simple latches or SRAMs, 60 type SRAMs or 80 type SRAMs, which are several hundreds of kilobytes in terms of size, sometimes often smaller. And their access latency is usually 1 clock cycle. And depending on the technology node and the technology, that could be anywhere from a nanosecond all the way down to 200 picoseconds. When it comes to SRAM, it's slightly bigger in capacity, but the basic structure is still 6 transistor SRAM that we are all familiar with. When we go to DRAM, that's when we go to tens of gigabytes, and then 3D crosspoint and storage go into the terabyte regime. The difference, of course, being that the access latencies are faster. This essentially enables you to cache some data at some of these faster memories while you wait for bigger chunks of data to come from these bigger, higher capacity memories. So at the outset, let me define some key figures of merit because they have a very big impact on how we end up designing these memories. So the first one is bandwidth. Bandwidth is represented in gigabytes per second or terabytes per second, and it refers to how quickly can I get the data and how much of the data can I get at the same time out of my memory system into the compute. The second one is latency. How quickly can I get that data from the memory onto my compute? The third one is capacity, which is how big is the capacity of the memory that I'm dealing with. And of course, bigger is always better because I can store more data and a variety of data. The fourth one is somewhat unique. It refers to the parallelisms of access. It implies that if, let's say, my data is distributed among 10 arrays in a memory subsystem, I would want to be able to access any bit and piece of that entire data set from any of these arrays at any point in time. And this can only happen if we have more parallelism in memory. And I'll talk a little bit more about this as we go through the slides. And the final one, which at least from the industry perspective becomes extremely important, and I would say that even from a technical perspective is a make or break for any memory, is cost per bit. How much money are you willing to pay in order to fabricate a single bit of memory? And of course, as we know, memories are created in tens and thousands of trillions of bits. So this is a normalized cost per bit. So let's ask the question, where is the computing need today? So I just pulled together some of these foils that were shown at Hot Chips conference this year by some of the Intel executives. And what we see is that earlier on, we were dominated mostly by Moore's law dominated improvement in the compute needs. But lately, we have been augmented, in addition to the Moore's law, with software and architecture-based acceleration. And this is what has enabled very high influx in the compute need increase. So this has been, of course, augmented significantly by memory as well. But nevertheless, regardless of memory, the need for compute has increased significantly, and it will continue to increase. So the next question you may ask is, if I were to plot the in general, what is the level of complexity of the problems that we are solving on the y-axis as a function of the performance? You will notice that as I keep increasing the performance of my system, the kind of problems that we can typically solve are not as complex, because the level of complexity of those problems is relatively simple. If it's just chess, you know that how many squares exist, how many pieces exist, what are their moves, and it's a simple algorithm based on decision making. Whereas when you go to more human type intelligence, that is when the complexity increases, and you can easily imagine that the performance gets constrained. The question is, what does the performance get constrained with? It gets constrained because of the high amount of data. You may imagine that as a human, we process a lot of data in our brains. We get tactile data from touch. For example, when you pick up a glass bottle. The second one is, of course, the visual. The third one is through your tastes or through the smell, etc. So you keep getting these five sense data, and that's actually very large in nature. And one example of why this data is large in today's industry is, for example, when Tesla or one of these car manufacturers, they try to make smart cars which are self-driving. When you try to do self-driving, you're trying to mimic a human while driving a car. And the amount of data you need to collect is actually ginormous. That is not very typical of most compute systems. That kind of data is usually dealt with only in data centers. And of course, a car is not a data center. A car just has a small computer. And you somehow have to make that data very efficient in storage and very efficient in access. So the question comes, where is the real gap? Can I find out the gap in this data explosion of how can I improve the compute? And that's where we hit the memory wall. So what is the memory wall? So if I plot the power on the y-axis and the system bandwidth on the x-axis, then if you want to get more data, which means more system bandwidth, you would, of course, consume more bits per unit time, right? And the energy to consume, to access a single bit is often referred to as energy per bit, units being picojoules per bit. And the bandwidth needs are, of course, in terabytes per second or gigabytes per second. Now, you can easily imagine that the multiplication of these two, the bit will cancel out, and you'll have picojoules per second, which is the same unit as power. And that determines the power budget of my system. Now, this makes it very clear that if I want very high performance out of a system, which is x-axis to be towards the right side, then I would also need to provide a large amount of power. And again, you can already see that the power numbers here are about 10x of what your laptop consumes. And certainly even a car cannot provide 10x of that power, right? So, so certainly there is a need for some intervention in terms of memory in order to improve this scenario, which is known as the memory wall effect, where my compute can be done very quickly, but the data from the memory cannot quickly get to the compute. And the reason why I cannot provide the data very quickly is because I actually can, through design, except the power just balloons out of proportion, right? So, so this is a fundamental conundrum. And it exists for each and every memory in the entire hierarchy that we discussed earlier. So now the question is, how do we solve it? Each memory solves it in its own way. So if I were to just summarize, what are the things that need to be improved? The first thing is we need to improve the energy per bit by reducing it. And this can typically be done by several components, and we'll discuss some of these components in the coming slides, all the way from bit cell level to the architectural level. And energy per bit is key, because if you do not have low energy per bit, even if you try to get high performance, you won't be able to provide sufficient power to your device, right? Because just imagine, again, just for fun, right? If we have 800 watts of power that we need to provide to give a certain bandwidth, and my devices are operating at 1 volt, then you can easily imagine V times I is power, right? So 800 amperes of current is what you would need, right? And that just sounds unreasonable and unrealistic that one is able to provide. That's like a power station, a micro power station. So, so energy per bit is really number one. The second one is increasing performance, which is through design. This is simple design. You improve clock frequency, you improve the parallelism through architecture, etc. The third one is improving the capacity. This is what the technologists do. They do this by increasing the density, and this is done through scaling. And scaling just means miniaturization, and I'm sure a lot of you here are very familiar with that. Another aspect that is often overlooked when we try to increase capacity is that it's not just that your memory has bit cells. It also has peripherals, which is the control circuitry that controls the bit cells. And it's very important that we take a very close look at these peripherals when we think about scaling the entire memory subsystem. And as I go through the slides, it'll be very clear that one of the key components is actually some of the analog components associated with the memory. And final, number 4, which although it is number 4, it's really from the perspective of industry, it's really the most important, because you would not build anything from which you would not clearly get a profit. Otherwise, you might as well buy it from those who can do it in a cost-effective fashion. So all of these goals need to be met while reducing cost. All right, so now let's dig in a bit deeper and figure out which of these components for typical memories make a difference. So I'm sure that a lot of you might already be familiar with a typical memory structure, but I would like to just reiterate so that we are all on the same page, and I make sure that no one is left behind in this talk. So the basic memory architecture looks somewhat like this, right? This is an array image. So what you have in this box is your cell. For example, it could be a 6-transistor SRAM, or it could be DRAM, or it could be a 3D crosspoint, or it could be a NAND flash, whatever. This is accessed using word lines, which are connected typically to gates of transistors. And the data is exchanged using the bit lines, which are these vertical lines that you see here. Okay. Now, of course, if you want to access a certain word, you need to decode the address. And that's what the address decoder does. In order to get the data out and process the data accurately, you need some sort of a cell input-output feature. And this is something that we'll discuss a bit more in detail in coming slides. But this is essentially what helps you mux the data out before you actually send out the final product, etc. And in terms of the physical picture, it would look somewhat like this, where the gray region is where all your bit cells are. The decoder will be on the left, and the cell I/O or the bitline peripherals, or the column I/O, also known as column I/O, is at the bottom. So let's one by one try to sort out each of these aspects, right? We first start with, I just have a single slide. I'll not waste time too much on the technology aspect, because I was told that that's not the main focus of this STTP. But I cannot stop without actually showing at least one slide, which is when we try to scale SRAM, essentially there are 3 parameters that make SRAM scaling challenging. It's not undoable, it is still possible, but these are the 3 important aspects that we need to be careful about. One is the variability in transistors. Imagine that the transistors are very small, where the LG that we are dealing with is of the order of about 20 nanometers or less. In that case, you have significant VT variation, which causes variability in transistors, which will automatically correspond to a signal to noise ratio and sense margin effects reduction. The second one is increased parasitics, and this is essentially because everything becomes very, very resistive when you go to very small sizes, and your choice of metals becomes very limited, and you are then limited by delays and parasitics associated with accessing your memory. And the final one is, of course, cost increase because you're now trying to make very, very small transistors. So certainly one of the key challenges is density. How do we miniaturize? And this is more associated with manufacturing aspects. The second one is the design aspect, and I'll just touch upon two brief points. And there are many design challenges in memory. We should not at all consider that these are the only ones, but this is just to give you a flavor in the interest of time. So again, what I'm representing vertically are my bit line and the complement. And there'll be some bitline circuitry like bitline recess, precharge, etc. You'll have some sort of a column mux, a sense amplifier that can sense the data, and finally some sort of a write driver. So typically you use a column mux. A column mux, what it does is just like any other typical mux, as we have all studied, it down selects all the data that's coming from my memory and sends out only the one that you are interested in, right? Depending on what is the address that you have provided. Now, this is a very important feature for most memories, because what this means is, let's say I'm only interested in one of these 4 bits that are being accessed. Number one, yes, I can get the granularity associated with a single bit in this imaginary word of just 4 bits. It's just imaginary cartoon word. But the downside is that I had to access all 4 bits because the word line, don't forget, is actually connected across the entire word. So I have to access all 4 bits, and I can only read one usable bit, which means I've wasted 4x the power to actually access the bit. And depending on which memory technology it is, the bit cell energy, which is the energy associated with just the access of the bit cell, may be significantly high, and I may end up wasting a lot of power, burning a lot of power, right? So this is one of the key aspects associated with design challenges. Okay, so how do you design memory? So you can have, let's say, this entire box represents my memory subsystem. You can either say that in order to get X number of bits, I'm going to partition it into 4 parts, which means I'll have X divided by 4 bits in this gray box, X divided by 4 in this, and in each other. Now you have the decoder and the column I/O on the sides and the bottom, right? And this is very area efficient because you're mostly trying to use the area for making the bits. However, if I want to get a bit from here and another bit from here, I cannot do it in the same cycle. The reason being that those 2 bits are not independent. They are within the same array. And at a time, an array can only access one or few word lines. Typically, in my cartoon construction here, just one word line in this entire gray box. I can, of course, parallelly get another word line worth of data here, but as I just defined, I want data from here and I want data from here, right? So I need both pieces of data from the same array. So this is not very good for it in terms of parallelization. And also, of course, it is slow because I have to travel long distances to get the data out. You can instead go for a highly partitioned memory in which for the same number of bits, you have many, many small arrays. And now you can get small chunks of data from each of these independent arrays. Now, the advantage is that I can get the data very quickly and in a parallel fashion. But the disadvantage is that I am increasing the cost because every time I have to stick in this blue and green, which are extra, which is other than the MB that you're buying or GB of data that you're buying, right? When you're buying 8 GB, you're not interested in knowing how much peripheral CMOS to access it exists on that memory. You're only interested in the capacity, right? So this is all wasted area, and that causes a cost increase. So typically SRAMs are highly partitioned and storage is highly densified, which is the previous case that I showed. So these were some of the design challenges, right? And this changes per memory. The final challenge is the energy challenge, and this, as I mentioned earlier, is the key challenge really. And in terms of the energy challenge, what we are looking at is we have our memory, which is right here. We have the I/O. The I/O sends the data across to compute. Now, if on a single die or a package you have both memory and compute, then you will have the within die energy, which is how to access data from the within the memory itself, which is bit cell energy, which is my 6T transistor. There'll be a gate oxide in each of the 6 transistors. I'll have to charge those and discharge those, and of course there'll be leakage power. Then there is the wire energy, which is you have to get the data from here, half CV squared, just simple half CV squared, get the data, let's say from here all the way till here, right? And along the way, you will have wires of different dimensions, as you know, hierarchical wiring is done across many interconnect layers. So that's another component. And finally, you have the peripheral energy, which is typically some sort of analog and mixed signal type systems, like you may have muxes, PLLs, charge pumps, and switch capacitors are a key component of voltage generators and charge pumps, etc. So finally, let's say you get the data out, then the next portion is the link energy. You have to actually get the data transferred from the memory, which is one square or rectangular box, to your compute die, right? And that's the bus. And of course, to drive the data across the bus, you'll have some analog drivers, right? So, so those are all the different components that go into the total energy of a memory subsystem. Now, in terms of future innovation, where does it lie, right? And this is the last segment of my talk. So the key question is, how can we make fast memories faster, denser, and cheaper, and bring them closer to compute to improve throughput? And there are some immediate solutions in the literature. One of the key solutions is that you go from 2.5D, which is memory and compute are next to each other. This could be at a motherboard level, or it could be at a package level. Package level implying that you have 2 dies, 2 chips essentially that are millimeters next to each other. So, so the link distance is very small compared to motherboard level, which is centimeters. So, so that significantly reduces the energy consumption. And of course, then there is also a 3D configuration. And this is often referred to as compute near memory, where the compute is placed very close to the memory. The distance between compute and memory is of the order of tens of microns, as opposed to millimeters in this case, and in this case, for example, it could be centimeters. So this is really bringing it to a different level. And in the future, this might be scaled to less than 10 micron regime. And again, why is this distance criteria that I just mentioned, millimeter, centimeter, so important? Because again, it all boils down to half CV square, right? You are going to transfer this energy. There is a capacitance associated with each trace, whether it is on the motherboard or 2.5D or 3D or anything else, right? And the shorter you make this distance, the lower the energy per bit will be. And that will help you design a better, tightly coupled memory compute system. Okay, so so there are 3 typical ways. This is what we do today. We just have a typical memory, and far away we have our processing. Compute near memory is some of these 3D approaches that I explained. Those are examples of it, where the memory is very close to the compute. And there is this third component that is emerging in the research area. And a lot of universities and to some degree in industry, there is research going on in this area where you're trying to put some of the compute functionality within the memory. Now, what do I mean by that? Typically, like I defined earlier, we just read one word line per memory array. This is just because if I read multiple word lines, I run the risk of contaminating the bits from the data from each other, right? So that's why I just read one word line, and the data is spit onto this blue-colored vertical bit line. Now, in-memory compute, some of the in-memory compute methods, there is a proposal that you should be able to read multiple word lines. You might contaminate the data, but some of that can be prevented by doing it sequentially. Like, for example, I read this, this particular word line. This bit line goes from a reference voltage of 0.5 volts to, let's say, 0.6 volts. Then I switch this word line off. Then I switch another word line on, and the voltage goes further from, let's say, 0.6 volts to 0.7 volts. And then I switch this off again, and so on and so forth. So by doing a sequential procedure, I'm able to get analog voltages onto the bit lines, right? And this is unlike typical memory read or write, because in this case, we are just using a small differential voltage and different amounts of differential voltages to get different states. So it's really like a multi-level state of the bit line. Now, of course, if you have multiple analog states, you need a method in order to differentiate between or distinguish between these states, right? And therefore, you'll automatically have ADCs. Now, as we all know, ADCs have very significant overhead in terms of the energy consumed for each conversion. And that is one of the key challenges of in-memory compute. But in principle, it's very powerful because if I can do the compute by the way of changing voltages on the bit lines, that has a significant impact on how we do compute, because we are doing the compute within the memory array as opposed to getting the data from the memory array, going to my processor, doing the compute there, right? So this is a very different paradigm that a lot of research is going into. And of course, as I said, the benefits are very clear. You can have multiple row accesses, and that enhances the throughput by a factor of how many rows you're accessing at a time. But in these components, you have a very big aspect associated with analog components. So really the grand challenge is, can we figure out a way to design AMS components such that we can retain the benefits of these multi-bit line reads? So, so this is one of the key aspects I think we have to always be mindful of whenever we use analog circuits in digital systems. It's very important that we make them very energy efficient, because they essentially are what can make or break a technology. So so it's very analog heavy in that sense. So with that, I'd like to summarize my talk. I hope I am on time. And today, what we do is the simple memory. This is what a lot of research in the industry is going on about, as well as this, of course. But really, the key bottleneck here is the design of analog components, right? So the industry is really interested in improving all of these, right? Because all of these will have their own places. The key challenges are, of course, cost and energy per bit. And when it comes to design of AMS components, analog mixed signal components, it's very important that scaled versions of these that can play well with digital circuitry can be implemented so that we can improve how we use memory or improve memory utilization for the future. So that's all I had. Unless there are any questions, I will stop sharing soon.
Any participant would like to discuss or ask anything to Dr. Abhishek?
Any questions from participants?
No, I don't think so.
Okay. Okay.
Okay. All right. Thank you. So I'll start presenting. Thanks a lot.
Thank you, sir, for sharing your versatile thought, starting from basics of memory hierarchy, memory design, challenges in memory design. To improve throughput of memory, you have covered a good flow of design structure. Increasing the computing speed of memory is a need of the hour. So thank you for accepting invitation and taking time from busy schedule as it is night time in USA. Thank you very much, sir.
Thank you so much.
Okay. So the roots of goodness lie in the soil of appreciation of goodness. These are the words of Dalai Lama. With this, I take this opportunity to put all my gratitude in the form of words. So on behalf of organizing committee, I would like to thank chief guest, Dr. Abhishek Sharma, who has graced this occasion with their presence. Then I would like to thank our respected principal, Dr. B.N. Chaudhary, for their guidance and inspiration, Dr. Rita Das, for accepting our invitation. I extend my sincere thanks to all the program evaluation committee members, Dr. B.N. Chaudhary, Dr. Deepak Karia, Dr. Reena Sonkusre, Dr. Sukanya Kulkarni, for cooperation, support, and inputs during planning phase of this program. I also extend my sincere thanks to faculty coordinator of this program, faculty members of S.P.I.T, non-teaching staff of S.P.I.T for enormous cooperation in organization of this program. Last and not the least, I want to thank to all the participants for showing interest for this program. I hope we will make this program successful. Thank you. Thank you all of you.
Yeah, I have messaged Maryam ma'am.
Okay, she's joining.
Yeah, she will join in a few minutes.
Okay.
So thank you, Abhishek. Thank you very much.
My pleasure. It was a great opportunity interacting with all of you and sharing some of my thoughts. Thanks again.
Sneha madam, you can go to the next slide, please. Anyways, I'm happy to see all the participants back from STTP1 to almost everyone is back here. I have messaged madam. Ma'am already joined earlier in the meet. She's busy, so she said to communicate back to me. So I have communicated. They're just waiting. So you can consider this kind of a 5 minutes break or something like that. So Madam will be joining in 2 minutes. Yeah, good morning, ma'am.
Good morning.
Yeah, sorry, ma'am. 15 minutes talk got extended. Morning.
It was this half an hour actually.
Yeah, oh, sorry. Yeah. Okay.
Yeah, my talk was supposed to start at 10 o'clock, which is okay. But as I told Priya, so this I cannot stay back more than the scheduled time. So therefore, I will shorten my talk and lecture accordingly.
Okay, welcome, ma'am.
Yeah, thank you. So you don't need to see my video?
Yeah, ma'am, I want to introduce you first.
Okay,
So
sure.
I would like to introduce. I would like to request Dr. S.S. Rathod to introduce our next keynote speaker, Dr. Maryam Shojaei. Over to you, sir, please.
So, welcome, ma'am, and kindly accept our apology for extending the earlier talk. So, it is my privilege to introduce ma'am, and as such, those who are present in today's meeting, they they do not need much of introduction. Everybody knows ma'am, but still, as a formality, I need to do that, ma'am. So, Dr. Maryam Shojaei Baghini is a professor at Electrical Engineering Department, IIT Bombay. She did BS in Electrical Engineering from S.P.I.T University of Paymal, and PhD and MS both in Electrical Engineering from Sharif University of Technology, and postdoctoral research at Department of Electrical Engineering, IIT Bombay. Dr. Maryam Shojaei Baghini is INAE, that is Indian National Academy of Engineering Fellow from 1st November 2020. Tata Trust Chair Professor for Fuel Engineering from 2020 to 2023. Joint recipient of Arun Kumar Choudhury Best Paper Award, International VLSI Design Conference India 2019. Impactful Research Award from IIT Bombay 2015. Recipient of the Richard Freeman Prize for the Best Paper at ICE UK, Journal of Emerging Materials Research in 2013. project guide and joint recipient of the first place award all over India in Cadence Design Contest India, 2 consecutive years, 2012, 2011, probably after that also, and project guide for one of the finalist projects in International Chip Design Competition in ISIC Singapore in 2011. She has got 120 journal publications and 155 conference publications. She has 11 granted patents and has filed 42 patent applications. She is the co-author of 3 books, Applications of Evolutionary Algorithms in VLSI, Hardware Development of Wearable ECG Devices, and Anodic MIM Capacitors. 27 chips have been fabricated and successfully tested by ma'am. Her research interests are, there are so many, and you know madam's research interest. Because of lack of time, I will not read the detailed profile. There's a big profile. Thank you very much, ma'am, for accepting the invitation. I'm looking forward for the session from you. And I'm transferring the access rights to you, ma'am, for sharing your slides.
Okay, thank you very much for the nice introduction, Professor Rathod, and also, you know, it's my pleasure to be invited for the keynote talk as well as giving a lecture in the STTP training course. And of course, thanks Priya as well. I know Priya. We work with each other, of course. And yeah, and all participants. So should I share my screen?
Yes, ma'am.
Okay, so I'll stop my video. How to stop this?
There's a button in the below side.
No, actually, it doesn't appear. That is the problem. Why it doesn't appear? Because it saves the bandwidth.
Yes.
Okay, let me see if I can do it from participant side. No. I don't know, somehow it doesn't give me access to stop my video. Anyway, so I share my screen. Oh, that also has gone. Interesting.
The sharing rights are given to you.
Yeah, but I should be able to share my screen, right? So
yes,
eventually, you know, the entire menu went off. Let me figure it out. How it is, where it is. Something.
Madam, then
I don't know. The entire control menu went off. I think I don't have any
Madam,
control
you
right now.
log off. Madam, then you log off and log in again.
Okay.
That would be better.
I hope I can log out. I think I have to close because there is even no now no control for logout. Let me see what can be done. I just closed the window. Okay, the menu went back. Thank you. Now I will share the screen.
Your screen is visible, ma'am.
Okay, very good. So I go to the full screen presentation.
Yes, it is visible.
Okay. So thank you for the attention and hello again to all participants, and thank you for the S.P.I.T. for arranging this talk. So let me start with kind of introduction to what is the topic of today's speech. Today's speech is eventually a review of, or eventually presenting 3 PhD research projects, which is done in our group. Why I am doing that? Because I want to eventually give you the kind of live demonstration. So it's always good to know that what is going on in literature and what is done by others, but at the same time, see that what can be done here. And then therefore we get the full confidence about a lot of things, good things that can be done by all of you. And therefore that is what we need also to, we can have our own also as a part of literature always. And this also helps you to get an idea about how to do a project here. And I think this will be useful because this course eventually, is about training. And this is a kind of training, I believe that, which will help you. And of course, what you see in these 3 projects, except one of them, the other 2, I have used Cadence tools for the design of the ASIC, and then of course we fabricated outside, and then we tested, and then we made the prototype of it. So let's start. So it is about, let me remove this. Yeah. So it's about sensor systems. So it's more about how to start from sensors and then design a corresponding signal conditioning and interfacing for that. You may say that, okay, so these are available. There are many commercial products that we can get. Analog Devices, TI, develop various boards and various ICs for this purpose. That's true. But with the expansion of the IoT, IoE technology, and which naturally has resulted in a kind of explosion of the sensor system area, still there are many gaps with respect to the requirements, so that you cannot get everything done by available commercial products. And the advantage here is when you start from some point and then for some application, if we look at a kind of, even national level activity which can be done, if you develop a kind of modular solutions which can be used, it's not a commercial product, but it can be used at least for research. And then later on, of course, as a part of translational research activities that we have, we can also transfer it to industry. We would get a better path for the growth in this area. And it's a time for that. And that's why I added this word growth to the slide. So it's about growth, not about what exists. It's about future and how we can be a part of that. So there are various applications, and this slide just gives you some examples of these applications. You may be familiar with this website, azosensors.com, which gives updates about the existing sensors and then what kind of sensors are developed, what is going on in this area. So it gives eventually as a kind of live journal about that. So you can get a lot of information there. So this is just to say that, okay, so there is a growth, and then we can be a part of growth. We can be a part of this technology and make indigenous novel products. And of course, all of them are linked to IoT, IoE. In fact, if there was no IoT, IoE, really there was not, explosion of this sensor system area. It started with the notion of connecting things. And because of that, when you connect the things, you want to get information out of them. Otherwise, what's the use of connecting the things? But to get information, therefore, they should have a proper kind of interaction with the environment in which they are placed. That could be human body, that could be a plant, that could be air, that could be soil, that could be even within a scientific lab where you don't want anybody to enter. It could be within an area which has to be disinfected. So anything. So therefore, they have to be able to have a kind of interaction and interfacing. And that is the reason that this IoT and OE is the driving force behind sensor systems. So I don't talk about IoT, IoE, and the standards, protocols, devices. My focus is more on the other side of this technology, which is about sensor interfacing and signal conditioning by looking at a very modular approach, or I would call it not very modular, but modular approach. And then what can be done? Sensors may not be very complicated, may be very cheap, may be disposable. And the reason is because this technology is becoming individual-centric as well. Of course, we need also to have IoT and IoE, for example, a fully automated, remotely controlled lab. Still, it comes under IoT, IoE. However, many of the applications which were not possible before, and now because of the progress in the technologies, which are not very expensive, we are able effectively get access also to the platforms which can give us the opportunity for fabricating individual-centric products. So individual-centric products need to be cheap, otherwise they are not affordable. And for that, therefore, the technologies also can be different. Disposal sensors or sensors which can be used for a short time or maybe a reasonably moderate time, and their lifetime is not very long. They become, of course, a part of the nature later because they are thrown out, and therefore the waste management and recycling of the material matters a lot. So that's why one side of this technology is the material and how it can be biocompatible, but I'm not getting into that aspect as well. But for now, let's look at only this kind of available sensors that can be used for various applications. But again, the focus is not about fabricating sensors. Focus about is how simple they can be, and they can be made in the lab. But then how to move forward, and then how to use them. And if we don't find a commercial product, which has been our motivation, how we can make our own design and then make it compatible with or better available commercial products. So therefore, both are possible. Make it indigenous, make it novel. Now, what are the components of the interfacing and signal conditioning? In general, you have several modules that work together to make this happen. You need a kind of sensing interface. This sensing interface can be as simple as a bridge, can be an oscillator, can be a simple divider, can be a very simple, say, integrator. It could be anything. Sometimes it's just simply a buffer. But finally, you need some interfacing. Sometimes it is actually a very, very well-controlled connection of an electrode to, for example, a conducting wire. That itself will define the interface, right? And sometimes it's actually the one ionic solution with metal interface. So this is what we call a kind of sensing interface. But then this sensing interface gives you some electrical signal which has to be conditioned. It cannot be directly used. And that is where we need dedicated, but at the same time modular and reusable modules. And then we come, of course, to digitization. The main reason is because the world of processing and data analysis is dominated by the digital technology. So therefore, we can go with digital conversion. Of course, I will add one point here, which is another part of the research that today I'm not talking about. We can actually go back to analog processing. In fact, analog processing now getting gain because of the notion of AI and machine learning. But I'm not getting into that. Right now, let's assume we have. Even if we don't have, so fine. So we don't need to have this analog to digital conversion. And we can right away go to the processing and data transmission. So I have not also included any processing here because this is more about signal conditioning. where you get the information and then you transmit them. Of course, if you want to do computation and processing at this node itself, or at the, what is called, say, something like edge computing, that's there. But again, I'm not talking about that because it's more about signal conditioning. And on top of all of them, you need to have a kind of power management and energy harvesting. These sensor systems are supposed to be power autonomous. We cannot have so many connected things, as it is called, Internet of Things, and each one of them need to be taken care by one person to charge it continuously. So therefore, this is out of question. All of them should have an arrangement for energy harvesting and power management, unless if it is for specific, well-controlled lab use, yes. In that case, you are not worried about electricity. Otherwise, it is a concern. That's why power management, energy harvesting, and energy harvester is a part of it. Now you see a lot of opportunity here, and I didn't get into the other part, which is processing, conditioning, decision-making. That itself also is providing a lot of opportunity. But here, because we are talking about design tools and cadence design tools, so I prefer to talk about the modules which are more towards the circuit design and system design rather than software and algorithm. So there are two ways to approach this solutions. One level is always to start with available components, not modules, and try to see whether using commercial off-the-shelf components, where we call them COTS elements, is it possible to make what I need? Is it possible? So we'll make it. If not possible, then let's make an ASIC, which will give what we want, and then we will use it. We will use it across various applications and various modular design of this signal conditioning module, and all the way to ADC and transmitter. And sometimes it's a combination of the both. So COTS elements as well as ASIC. So for partial solution will be ASIC and the rest will be COTS. So what is eventually requirements? Requirements is it has to have a very wide range. Why wide range? Because you want to reuse it as much as possible. Therefore, you cannot have a signal conditioning circuit for each and every sensor, which in each and every range of sensor. So you may have even one type of sensor, but with different values of the, sensor range, which makes it different models of that particular type of sensor. But you don't want to make it the same thing for the signal conditioning circuit, make different models of them. So it's not a viable solution. So we want to have a system or ASIC which can work with a wide dynamic range. And it can be eventually it will have a wide dynamic range, which can be used for wide dynamic range of sensors. Many sensors have non-idealities, so we need to deal with these non-idealities. They are not at all ideal elements. And the third part, of course, we want always to make them low energy. Having a low energy, low has its own meaning. Sometimes milliwatt is low, sometimes milliwatt is high. Sometimes microwatt is low, and sometimes microwatt still is considered high. So it's a relative notion, but in the context it is used, it has to be as much as possible energy efficient and low energy, both together. And that's why power management plays a vital role. Recharging is an issue. If there is a recharging has to be done automatically using available resources in the ambient or in the system itself. So we cannot afford manual charging in the systems. So I start from a simple capacitive sensor, and with a simple example of non-idealities, which is a leaky capacitive sensor. Leaky capacitive sensor means it has a parasitic, eventually resistive path, which results in passing current, right? So it's equivalent with an RC circuit. So as analog designers, we always make the simplest models. So this leaky capacitor that we are talking about is one of the capacitors that already fabricated in our group. And even we had a workshop in the December Spark workshop. A similar technology was used to actually train BTech students from participating colleges to actually make them in the lab. So it was paper-based. So this means that, we just use it to just demonstrate to them. They can actually see how, when they keep it in front of their mouth and they just breathe, how the value of capacitor changes. It's as simple as that. In fact, it can be accommodated in the mask, and mask can be used. But it's a very simple process of fabrication. So it's easy to make. But when something is easy to make, that means that it's not very sophisticated. Yes, so it's a leaky capacitive sensor. But instead of adding to the complexity of the fabrication or going with more expensive platforms, of course, anybody can make very accurate capacitive sensors, but at what cost? Why not to push the complexity to the other side and then see that what can we do at this circuit side to take care of non-idealities? So this is a very simple fabrication, which is based on eventually a paper stencil. It's an interdigited structure. And at the end of the day, you will get a simple fabricated sensor using this paper platform and using some simple way. For example, it could be patterning with laser, it could be screen printing, but you will get this interdigited structure, and then by connecting wires to the electrodes, you will get some reasonable behavior from that, right? But now how to deal with this, right? So that's the important point, because it's leaky. And I'm showing the references here, and I have chosen all recent work. So therefore, you can see that all of them are published in 2020. So that you have also some idea about then what can be done, even it's very recent. So this is practical. So we make a small model of this sensor. Okay, so it has parasitic capacitors, CP1, CP2. It has a leaky path, which is shown by Rx here. And it has some base capacitance, which is C offset, but information actually is in delta C. So it's a simple electrical model, which is very much convenient for everybody. But at the end of the day, out of all this, in fact, here you see 5 parameters. And out of these 5 parameters, only one of them is information, and all other 4 are eventually extra redundant information, which have to be eliminated somehow. Otherwise, see, it's difficult to extract 1 out of 5, right? And that is the problem with many of these sensors. Okay, so now how to deal with that? So one of the techniques that works well in literature, and it has been used for various applications, are fully automated feedback-based, linear control feedback systems. Fine. The second point in these feedback systems is if we can make the system in feedback loop in such a way that the steady state error approaches to 0. That can be done using an integrator. If you put a kind of integrator in the feedback loop of any linear control system, you are able to make the steady state error to 0. Now, we add one more concept on top of that, which is called auto-nulling. Auto-nulling actually uses the same concept of bringing a steady state error to 0. And then we now make the concept. Can we use this leaky capacitive sensor, but make it in such a way that finally we will get only information about imaginary part of the impedance? This is one thing. Therefore, we can remove the effect of Rx. What about parasitic capacitors? So parasitic capacitors can be eliminated if we try to make the nodes associated with them to be set at a given voltage. Yeah? This is second. The third thing is about offset value. Can we make a kind of reference capacitor which can be adjusted in such a way that this auto-nulling loop itself allows us to set the right element. So these are the three kind of approaches to get rid of this four non-ideality related parameters and reach to actually what we want. Let's start from the interface. This is what eventually I introduce as a kind of interface with the sensor. This is interface. Why? Because this is a sensor, that leaky sensor with a non-ideal model. On the left side, you will see a simple inverting amplifier, right? Made using an op-amp. And you can see these two parts are kept in two sides of a bridge, right? And then you have one more side, which is eventually a simple multiplier. And this multiplier has two inputs, right? It's an analog multiplier. So this analog multiplier actually receives the output of the feedback circuit. So therefore, we want to create a kind of feedback so that this loop, feedback loop, whatever it is, will settle at a steady state error of 0, which is usually the input of the integrator. Therefore, output of the integrator in a steady state will settle at a constant value. Therefore, multiplier eventually will give information about only this CS, because we excite this node using an external source. It just got inverted, comes here. If the other input of the multiplier approaches to a constant value, so the current which flows through this capacitor is indeed proportional to the capacitor. And this capacitor is a reference capacitor. So therefore, this can give us a way of comparing the current which is coming from the sensor branch to the current which is coming from a sensor reference capacitor. So how this is done? So because we make it inverting here, so therefore effectively here we will get the opposite sign, and that works like a subtractor. So this current, comparison of these currents eventually is a current, that subtraction, which eventually goes to a current to voltage converter, because we want to make everything to be done in voltage domain. It is easier because right now we are using quartz elements. So these are elements, as you can see, you can make. These are resistors, these are op-amps, so it's very easy to make it. And these are interesting projects. These are new. In fact, the circuit is new and it's published. So therefore, I just want to show you that you can always start with what is available for you. And what matters is only how to design. Okay, so this is one part. Now here we use the concept of, modulation. You know that if you have an impedance and you want to measure real and imaginary part of the impedance, there is a technique to extract the real imaginary. It can be done by software, it can be done by hardware. So here we do it using hardware. So it's eventually you generate a quadrature version of the same input. This is a sine wave, a single frequency, single tone sine wave. And then you use, this is a kind of chopping, or can be also considered as a multiplication. This circuit, which is called zero crossing detector, is only for converting this sine wave to square wave to derive the switches in this chopper. So this switch either is in the upper mode 1, or position 1, when you get the signal, or you get the invert of the signal. So it's like you are multiplying by a square wave with a 0 DC, and it has bipolar value, 0 DC. So therefore, like 1 minus 1, something like that. So you are multiplying. So this technique of chopping using the quadrature phase allows you to extract the real and imaginary. Now, if you use this quadrature phase and switch, you will get the imaginary part as a DC. So that DC will be extracted using a low pass filter and will be given to integrator, which has the job of bringing the final error to 0. So nulling comes over here. Nulling means that this loop will settle when the input of the integrator approaches to 0. And when input of the integrator approaches to the 0, exactly what we will have at the output of this sensor, which is output voltage. So this will settle to this value, right? See, this is eventually if you write equations, so because we are having the subtraction, so naturally you will get the subtraction of the two parts which are related to imaginary currents coming from here, Ix and Is. One of them is, of course, proportional to Cx, and the other one proportional to Cs. These extra coefficients are coming because of the multiplier coefficient that we have, and it is appearing as 1 upon k. And then we have the value of Vsense. But this is because of the loop. But mainly it's eventually comparison of these two components. So in the steady state condition, output of low pass filter approaches to 0, which we call null condition. That means effectively at that time, value of Cx is equal to this value, which is Vsense upon Kcs. That means that we will wait for this loop to settle. When it settles, output of the low pass filter will go to 0. And therefore, we are able to measure the Vsense over here, right? This is Vsense that we are measuring. So this Vsense will give you, by just measuring Vsense, and k is already known because k is about multiplier coefficient. Vsense is measured. It's just a simple DC value. It's as simple as measuring a DC value. And you know value of Cs. It's a very nicely, very carefully measured capacitor, and very precise capacitor with a very low temperature coefficient, low sensitivity to humidity. It's a very nice reference. This you can purchase because this can go with. This can be, in fact, the expensive part of this whole system, but it is not still very expensive. So then you indirectly get the Cx. So, this is just using several ideas combined in one single idea and then get this circuit. And this nulling, in fact, is used even in many commercial instruments, lab instruments. So this is one single example. So it gives everything now, right? So because nothing appears here. In fact, if you notice, this parasitic capacitor is connected to input, which is already driven by an external source. The other side is connected to a virtual ground. Therefore, in this way, we are eliminating the effect of parasitic capacitors as well. Okay, so this is the first example. And if you want to know that how to generate this quadrature phase generator, so you can always use a commercial IC for that. But here, actually, the Shahid, who is the PhD scholar, and this is one of circuits that he has designed as a part of his PhD work, he developed that circuit also using COTS elements. And it uses again the same concept to generate this quadrature phase, and again same auto-nulling. That's very interesting. And here at the null condition, the phase exactly gets adjusted at pi/2. So, and then again here you can work out the equations, which eventually gives you the same thing. So here you have the similar arrangement. The low pass filter followed by an integrator. Here you have the chopper, and again it is 1 - 1 chopping. And here effectively you have the similar arrangement that we had for the multiplier. This is eventually a high pass filter. So this high pass filter will give you no change in the magnitude, but it will give you change in the phase. And when this loop settles, the phase shift becomes pi/2, which is phi. So that's the interesting point, that the same idea now is used also to generate a quadrature phase. So now you put them together, effectively you will get a whole schematic, which is shown over here. So this is a simple example to start with, and then using it for applications like, say, water level sensor measurement. In fact, it is used for measure the level of the water in the tank, which is in one of the buildings in IIT. And this is that auto balancing circuit, which is a simple circuit made on the, but it's a novel circuit. You know, this is important. Making something which is modular. This is really modular. If you look, you can just use it because it has a very well-defined concept. It is relatively affordable. It can be fabricated in a very, you know, dense, small form factor, because you can use, say, quad op-amps IC. So therefore, it really becomes very, very compact solution, and then it can be reused. And overall performance is reasonable and a wide range. In fact, wide range of the input can be easily achieved by just changing CS. Imagine that you can just simply change the CS. So therefore, still you will have the arrangement for making the different programmable, eventually, bridge. This modified bridge is a kind of modified bridge, is a new bridge arrangement. And again, if the capacitor you add has some parasitic capacitors, shunt parasitic capacitors, they will not have any effect on the measurement, because one is driven by the multiplier and one is connected to the virtual short. So therefore, only float values, or eventually node pair capacitor between a pair of nodes, will be measured. Okay, so I just, in this table, which is the comparison with the existing prior art, I talk about this range, which we can easily achieve this range, which is almost like, you know, it's almost like from 50 picofarad, say if you go to 50 to 5 nanofarad, so it's almost like 100 times more. And amount of relative error. If you use relatively elements with a minimal tolerance, you can achieve the very low relative error, because nothing is manual here, and still you can achieve a very reasonable range of the input with leakage. And this, you know, leakage range is right now in our setup for this spec is 100 kilo ohm to 10 mega ohm leakage resistor. And this is one of the best numbers reported using commercial off-the-shelf ICs. Output is analog, so it can be used in any manner which is required as per the next circuit. Power consumption is not under our control. This is one of the things that you see in most of the systems made using COTS elements, because you don't have any control on the power which is drawn, or even the supply which is required. It is defined by that component. But when we go with ASIC, we have more freedom, and therefore we can make a low voltage, low cost version. Okay, so to summarize, this is a very simple example. It's circuit level. Still, I have not reached to ASIC, but we will move on with another example, which is ASIC. But to summarize, it is good for leaky capacitive sensor applications. It has relatively wide dynamic range. Even quadrature phase shifter is using the same concept of auto nulling, and therefore, and it's fully automatic using a linear feedback loop. And it has relatively good accuracy because of this auto nulling and automatic feedback loop, which adjusts the final error to very low value, close to zero. And then power consumption, by choosing the reasonable elements, still you can get the reasonably moderate power consumption, because it's not under our control. We just need to choose the elements and whatever is available in the best we can. So now let's move on to another example, which is another dimension. Why I say another dimension? Because here we look at a novel design. It's modular, using COTS for a leaky capacitive sensor, because we want to talk about disposable or short lifetime sensors, which are good enough for many applications. When you want to measure the level of water in a tank, 0.2% error is absolutely fine, right? So it's not at all important. In fact, more than that error also still is okay. Therefore, it can give you a more accurate more accurate applications. For example, imagine that we are measuring the quality of the water in a remote area. A remote area means remotely controlled area, not necessarily remote area. Suppose, for example, close to a river or a channel. And then suppose we have a system which is automatically sampling the water. In fact, we have one other project which is going on in this direction. So when we pump the water gets into the containers, small containers in the system. We have to make sure these containers are empty, right? There, for example, when we look at this kind of applications, we need to know that how much real content is empty. So there, maybe 0.2% is really required, or even sometimes less than that. Because if the container is not completely empty, the next measurement may get affected. Of course, we have the provision of washing these small containers every time before again new reagents arrive, and then sample is pumped to the container. But what I mean is that there are various applications that one can think of which will need more accurate measurements, and therefore with AutonoLink we can achieve that. Here now we go into very precise, so it's other dimension. Suppose now let's, instead of capacitive sensors, let's look at resistive sensors. And let's assume, because one example was how to handle the non-idealities. This example is an opposite way. It's a resistive sensor with parasitic capacitors. But here now we eventually make it very accurate. So that means that a resistive sensor, and we want to have a measurement of better than 100 ppm variation in the resistive sensor. That means resistance changes, and we want to measure it with accuracy better than 100 ppm. How to do that? So here we actually look at the basic solution. So because COTS solution doesn't give us what we want, and therefore we start a similar concept, but this is now at the ASIC level. So here again we have the interface. This is again another kind of bridge. We call it half bridge. It's just like you cut a bridge, or you can call it full bridge when two branches are actually current sources. And these current sources are square wave generators. By the way, before I continue, to make the session also more interactive, because it's modular. In fact, presentation also is modular, 3 parts. If you have any question, you can ask with respect to the first part. Then I move to the second part.
Any participants and any questions? Then maybe they will ask at the end.
Okay, no problem. So
yeah,
we will move to the next part.
yes.
So here, let's start again from interface, but keep in mind here now we are talking about chip design. So it goes into that. Sensor part, of course, is outside. Again, we have a reference sensor. And then here you can see the parasitic element, which is capacitor now, right? Okay, so we have these capacitors. We excite this reference resistor and the sensor resistor using 2 current sources, which are AC current sources, square wave current sources. And the frequency of this square wave is F mod, eventually F modulation, because it's like you are modulating the information, which is inherent, the information is in RS. So we are modulating this information, converting it to a kind of, square wave voltage over here. So that's why this input voltage of the system also is called V mod. So it's a circuit on the chip. This part is these 2 resistors are not on the chip, but the rest of it is on the chip. And this is V mod is eventually differential input. If the two resistors are exactly same, this input will be 0. So, but if inputs are not same, so we need to see what will happen. And that's why output eventually, this is an amplifier, it's an instrumentation amplifier. So output will be eventually the amplitude of the current multiplied by the gain of the amplifier multiplied by Rs minus Rf. Eventually I multiply by Rs minus Rf. Rf, I is amplitude of the square wave multiplied by A will give the DC output. Why do we have this module over here? What is this? This is the same chopping. Because when the voltage arrives here is a square wave. Therefore, you need to apply another square wave to de-chop it. Eventually, bring it back to the DC level. So you apply to filter, but if you use an ADC with anti-aliasing filter, filtering automatically is done. And therefore, you will get again an analog output. So therefore, the common point between this ASIC and the previous circuit is the output is an analog voltage, a DC analog voltage. But measurement is done using the AC input. One of the advantages of using AC excitation for measurement is that you are not, the measurement is not sensitive to the DC errors. For example, suppose if the temperature at the bridge, because we are talking about 100 ppm change. Suppose temperature on the left side of the bridge and right side of the bridge are slightly different. And then what if the temperature coefficient of these resistors are not exactly same? So some DC component is produced because of that, and it will change with temperature and time. So that also will be measured, and it's very difficult to discriminate them from each other. That's why we usually modulate the input, or we give an AC input, so that, and this frequency is not too low, so that the low frequency variation due to ambient will not have impact on the measurement. That's the reason we use, and in the previous measurement also, of course, it was a capacitor anyway we needed to apply a AC signal, but in general, we don't use DC sources. As you can see, we don't apply any DC input for measurement. So DC input application to a bridge is like a textbook context. It is not a practical, unless if it is used for very low accuracy measurements, for low accuracy measurements. Okay. Here now, what is the effect of parasitic capacitance? That's very important. Let's assume this is one simulation we chose. Suppose if we have a delta R by R of 1 ppm, how much would be the calculated delta R by R if we have parasitic capacitor and with respect to the frequency? So reference resistor is considered 500 kilo ohm, and it is and the error due to parasitic capacitance is shown over here. If you go with frequency of modulation frequency of 10 radian per second, we get 0.01% error. If you go with a frequency of 100 radian per second, we get 1.6%. If you just go with a frequency of 1 kilo radian per second, this is just a ratio of 10, we get close to 55% error. So that means that this measurement, which has to be done in AC mode, is very sensitive to the frequency of the modulation. So the first conclusion here is, if you want really to go with actual measurement, which is high accuracy, we cannot afford to go with high frequency. So we have to go with a very small modulation frequency. But you may say that, okay, what is the problem if we go with a small? Of course, this small is not so small that effect will come, right? We want to make it small enough so that this effect will get eliminated, but we don't want to use DC. DC also has its own issues. Low frequency, temperature dependent variations will come to the picture. So it is high enough with respect to that. Fortunately, frequency due to temperature variations is too low, right? It's too low. It is in the range of, say, millihertz. So therefore, this F mode is not so low that millihertz, right? This is 10 radian per second. So it's in the range of hertz. So therefore, we need to do that. Otherwise, we can't. But other parameters we can, because we can make the system fully automated the same way that we talked about the previous example. And now here we can add low power, low noise requirement as well, because now accuracy has increased, because now we are able to get better arrangement with ASIC and custom design. So one of the problems when we move to low frequency is flicker noise shows up, right? So if we want to operate a system at very low frequency to avoid effect of parasitic capacitors, or at least make them negligible, then we have to take care of flicker noise. So you may say that, okay, this flicker noise inherently is taken care, but be sure that actually here there is a problem and there is a trade-off. We have already a chopping happening because of a square wave, and we have a chopper at the output. So, and equivalent input noise of INA, instrumentation amplifier, can be shown as an equivalent input noise source, shown over here on the left side. So if we have this kind of arrangement, so we can have the, naturally we see the concept that you see in up converter, down converters in wireless transceivers. So when you have a multiplication, it's like a mixer, right? Mixer is a multiplication. So if you look at the noise floor of the flicker noise, when you, there are two things. One is the input signal, which is coming from bridge, and it is getting chopped effectively, right? So now what will happen is, let's look at a simple, let's forget even about the bridge. Let's assume that we have just a simple DC. We just chop it, apply it to instrumentation amplifier, and then dechop. What will happen for noise spectrum? Input signal, say, is DC. So when we chop, so this DC signal is moved to some frequency, which is up converted to F mode. But noise is not up converted, because noise is off that. Therefore, output of the INA, which has noise and up converted input signal, will be again down converted. So, so when we down convert, see, every down conversion or up conversion has equivalent down and con. When you multiply two frequencies, you will get omega 1 plus omega 2, and you get omega 1 minus omega 2. So both of them appear. But by filtering, you can choose one of them. So here there is no such filtering here. It's just components are generated, both. But when we dechop, so a low frequency component is generated, which is eventually up conversion, down conversion. So input signal will go back to the original value. But the noise which was here will be up converted because of the second chopper, but it will remain because noise is exposed to one chopper and input signal is exposed to two choppers. So you see the spectrum over here, which will be helpful. Now, if you apply a filter, you would be able to get the input. But the point is that this filter, of which, you know, this, for example, the characteristics is shown here, can also get some part of the inertia of the flicker noise if this modulation frequency is not very high. And that is exactly the problem we have here, because we concluded due to parasitic capacitors, we cannot go with a very high modulation frequency. Therefore, we have to reduce the modulation frequency. But if we reduce it, then we have problem with the flicker noise. This problem exists here as well. The only difference is, instead of having DC input and chopper, they actually put the chopper at the bridge itself. So the spectrum remains same. So this is the conventional method, which is problem. In fact, we have published this work using Coates element a few years ago in IEEE transaction on instrument measurement and instrument, theme, transaction and instrumentation and measurement. But this work we published this year in JSSC because it's actually a new way of looking at this method. our own method, we have made it now better with respect to this dilemma. Therefore, there is actually a noise error trade-off. So we have problem. Flicker noise frequency F mod should be high. Error due to parasitic capacitance F mod should be low. So how to solve the problem? And this was the second PhD topic to solve the problem. And this is the way Meraj looks at the problem. So what he did is that he added one more frequency. And then now we have F mode, and then now he added a new frequency, which is called F chop. Now we have two choppings and two mixings, and eventually two sets of up conversion, down conversion. Now F chop is high, right? Because already when V mode arrives here, already effect of the parasitic capacitor has gone away, because information is kept in V mode, which has a low chopping frequency or low modulating frequency. The second modulation frequency is high. Therefore, flicker noise now moves to a very high frequency. So, but what is the penalty? Penalty is now we have more choppers and more switching noise. In fact, reviewers also refer to that. And then they also explain that the whole novelty that we have not only lies in this, but also lies in how to reduce the number of choppers. And what he did, he actually combined them in one single solution. Here you see there are two choppers in cascade with two chopping frequencies. He showed that if we mix these two using a simple XOR, simple single gate, we can remove one of the choppers. And therefore we will end up with a number of choppers similar to the conventional case, just one chopper extra. And this was a very nice and beauty of the work he did. And he showed also, if we compare with the conventional methods, which is that one of those conventional methods is our own previous work, the proposed method can reduce the noise floor by the ratio of this F mod upon F chop. In fact, if they were same, ratio was 1, so no improvement. Now we can reduce it. So by this arrangement, we went with 100 Hertz for F mode and 10 kilohertz for F chop. So problem is solved in this way. The second thing is about INA topologies. Which INA did we use? We didn't use 3-op-amp based INA. We didn't use capacitive feedback INA because of different problems they have. But we use current mode INA, which is in fact, current mode INA is the INA I have used from past, for example, 10, 15 years. And I have found that it is overall performing well compared to other two INAs. And we have variety of these INAs now. And Miraj made another version of them by using this chopping. So this is eventually now this CMOS circuit, eventually the INA circuit, and choppers are embedded within the INA. We have also 3 levels of the current generator, fine, medium, and coarse. This is for automatic adjustment because we don't want anything to be manual. So you can get details of the noise analysis, details of the analysis of the circuit in the published paper. But just simply to give you an idea, it is based on this concept. You eventually convert the differential voltage into current at the input. Then use a kind of current mirroring or current transfer and convert it back to the voltage at the output. So it's a kind of GM stage at the input, a kind of current mirroring, and then transimpedance stage at the output. So this is the whole idea. And each one of these stages uses its own internal feedback so that the gain of INA is very well adjustable and is fixed. It eventually becomes the ratio gain, which is immune to process variations and temperature variation. And this small part that with red color you see here, this is another innovation that he used for making a cascade current mirror to be very precise and independent of the mismatch of the VDS of transistors, which creates a mismatch in the between the current. So in this way, this part also is another novel contribution to this work. So to summarize, this gives you now an idea of the whole system. And the one which is shown by the gray color is on the chip. So this is the current generator, chopper, and then XOR that I told you, and then the choppers which are at the input and output of INA, which is eventually merged, as I told you in the showed you in the previous slide. This is on the ASIC. This is the half bridge that we have, sensor, resistor, and reference at the output. And then this is, of course, ADC with anti-aliasing microcontroller. We have a digital filter as well to get the precise ratio measurement. In fact, this ratiometric measurement, which is shown over here, helps us to remove the effect of even internal mismatches. So we have a 4-phase measurement effectively. First, to set the range to get the maximum sensitivity, so I value will be set. The second is making value of RF to be compatible with RS. And then we will take care of the offset calibration, which is due to the mismatch of the base value of the RS and RF. And then finally, exposing the sensor to the actual parameter and measuring the delta R. And then this differential and ratiometric operation, DRO, is resulting in this equation. And in this equation, everything is already measured. Therefore, when we want to get delta R by R, effectively, we don't have anything which is not known. So automatically system, in fact, system does the calculation and give us the value of delta R by R from this equation. And this is very, very useful because now many of these parameters are eliminated. For example, D factor, which is due to higher frequency components, is eliminated from numerator and denominator. So it's very helpful. So even see, this blue terms are eliminated. So it's very interesting. Even the gain of the INA is eliminated from the final measured value. So this is automatically given the system. So as you can see, the system also has the feedback loop. One is for the controlling the value, and one is in the 2 modes, because one mode is for the sensitivity measurement and one mode is for RF arrangement. So a switch is kept over here, which creates the 2 modes and controlled by the controller. So therefore, here again, user doesn't need to be worried. This is one thing that is one of the philosophies now I'm following. Try to make everything as automated as possible so that the system is smart enough to take care of everything. And partially hardware and analog design and partially software. Okay, so this is the actual ASIC fabricated, and these are the modules on the chip. So we have current generator, which is over here, and then instrumentation amplifier over here. We have 2 of them because it's the 2-channel measurement system, and we have some digital modules on the chip, shift registers and other digital blocks, which are shown over here for the testing purpose and control. On the board, which is still not a very large board, you can compare it with the size of this package and size of these switches and connectors, you can see. So it's not very high. This is actually the power management part on the board. These are the capacitors and variable resistors outside. This is all for adjustment. But main modules are, one is the connector to the sensor. This is that ADC, which is outside. This is the controller. And this is ASIC. And a small power management to keep the regulator and other parts available on the board. So now what we did is that we used it with a strain resistor fabricated by one of my collaborators, Professor Masood from Michigan University. They work on the fabrication of sensors. So we got that sensor from them, and then we measure the values. But before going to that, I show you also a kind of comparison with the commercial instrument. That is what I told you. We can compare with commercial instruments and then see how well we can achieve. See, we have LCR meter and we have our own proposed system, right? So we have done 3 measurements, and this is done by the eventually the deflection of that sensor and delta R by R in ppm, which is observed. And then you can see the dotted line, dotted eventually line shows the value, shows the values which corresponds to the connection of points due to the values we get from LCR meter. And solid lines are due to the connection of points we get from proposed system. So this is really very nice match. So it's matched in the sense that we really have a very small negligible error with respect to LCR meter. And here you can see the measurement when there is no parasitic capacitor, very small parasitic capacitor, and then when unproposed, some parasitic capacitor of 56 picofarad is added, which is relatively very high value as well. And then here I have highlighted what is achieved with respect to the other ASICs reported in literature. It's a very compact design, even though we are using similar technologies. Design is very compact, very low area. Base resistance has a very wide range as compared to the reported works. Maximum delta R by R, because we have a large dynamic range, right? So, and because we have a wide range of the inputs, so at 2 values it's reported, 10 kilo ohm and 0.5 mega ohm. And for each one of them, you know, we have corresponding I. I told you we have the automatic adjustment of the I depending on the value of RS. So this is the maximum value which can be nicely measured, plus minus 135%. From the lower side, we can go down even to reporting 26 ppm for 10 kilo ohm and 72 ppm for 0.5 mega ohm, with the corresponding currents as low as 100 nanoampere for excitation. CMRR of INA is the highest reported across other reported works, better than 110. These are all measured values. It's fully automated. None of the reporting works are fully automated. It does everything. It does calibration, which is eventually removing mismatch effects. It does everything and just gives you the final output. And we have also, as I told you, because we use AC excitation, we don't have any problem of the EMF effects due to thermoelectric effects at the interface. And parasitics are considered, and therefore it's a complete, well-defined set of achievements which is useful for many applications. This kind of IC is not with the requirements we had, we could not find in the commercial products. That's why it's very important to see that what can be done in a modular way. So to summarize, so it's very suitable for resistive sensors with parasitic capacitors, right? So this is the ASIC now we present. It is again fully automated with fully automated calibration. It has a very high resolution. Target was 100 ppm. We achieved better than that. Dynamic range is very high. We can go as low as ppm to more than 100% variation. It's a wide range of delta R by R with a very high accuracy. Okay, so do you have any question for this part?
No question, ma'am. Right up to this point.
Okay.
Anybody any question? Participants? No, okay. Continue.
Okay. So the third one is still an ASIC. Now we are getting into digitization and energy harvesting, because I told you these are also other modules which are any limitation of the current mode operation. Actually, everything has its own limitation. So one of the points that you need to be concerned about in current mode INA is you need to have the gain of internal feedback loops. Okay, so I don't have details here because this is not about really going into details, but I will try to explain from this schematic. See, if you look here, you can see an internal feedback. So let's start from here. This is, of course, the chopper. But after that, this is high frequency chopper. After that, what you see is these are two buffers, right? An output from the drain side is fed back to this circuit. I mean, all the way you go ahead, come here, and then reach here. So this is the feedback loop. One of the main points in the design of this current mode INS is the loop gain of this local feedback loop should be high enough. Otherwise, you will have some error. Because what we want, why it is the case? See, what we want this input voltage, which is applied to the gate of these transistors, to be over these resistors. Means the differential voltage, which is induced on this M1 and M-1 should be very low, so that you have a perfect voltage to current conversion. In fact, in this schematic, these buffers are shown, right? There you see those source follower transistors. And gain of these buffers is shown as 1. That means the input voltage you want directly to get transferred to two terminals of Ri. Now to do that, you need to make sure the loop gain is enough high. Now to make a high loop gain, you need to take care of the stability of that. Because when loop gain is high at low frequency, at higher frequency, still loop gain is very high. I mean, it's not at least less than 1. So therefore, it has to be stabilized. That's why we use these capacitors for compensation and stabilizing the loop. And we need to really arrange a very high gain within this loop. So this is one of the, and same thing happens for the output part. So this is one of the challenges in the design of current mode INS. But overall, still I have found, in spite of these challenges, still they are good for low power applications, and they are able to give a very nice CMRR. As you can see, our measured CMRR is better than 110 dB, because they don't have too many elements that you need to be worried with respect to matching. Look at here. This RF should be matched with this RF. This op-amp has to be matched with this op-amp. Here, these capacitors have to be matched. These resistors have to be matched. These capacitors have to be matched. More matching elements, more degradation in CMRR. That's why the problem in both cases is CMRR depends on matching of the elements. Here you can achieve high CMRR without being worried about matching. I mean, it's not like perfect matching also is achieved here, and there is nothing that you are worried about mismatch. Still, you have current mirrors. And current mirror, you have to make sure that, you know, the gain of the current mirror is controllable. And then from both sides, because you have two current mirrors. So still, you know, inherently here also you need to be concerned about the matching of these buffers, right? And because this is a kind of differential current, so you have effectively two current mirrors inherently. So that matching also need to be taken care. But overall, my experience shows it is more controllable. It is more controllable because effectively you don't have any op-amp even in any one of them. In this case, you don't need a really op-amp as such to be used. It doesn't use op-amp. So therefore, that another advantage is that it gives you a very nice control on the noise. Of course, you can make also this on the chip and make an op-amp on the chip. But then you have to take care of all requirements of the op-amp, including CMRR of the op-amp. So that's why this design gives really high CMRR. In my experience, I have got always a very high CMRR in this design. And yeah, that's it. These are the kind of, the only thing is you need to take care of this buffer to give you almost gain of 1. That's why this loop gain matters a lot. This loop gain should be very high so that the drop across the VGS of transistor source followers will be low. But this can be taken care. It's not like it is not manageable. It can be taken care. And by having this automatic calibration loop, that helps a lot to get everything adjusted well. Of course, we don't have as such any adjustment on the chip. That's an interesting point. Because we have this chopper, you can consider mismatch also as a kind of very low frequency noise. And that will get up converted. That's why we reduce the effect of mismatch by this arrangement as well. And always you can use dynamic element matching, which is a kind of chopping, to reduce effect of mismatch further. Okay, so now we go to the third part, which is energy harvesting and ADC. So now here, example I give is the biopotential acquisition systems, multi-channel, and for a very wide range of frequencies, which cover almost most of the medical applications, almost, not all. And here, because again, we are talking about the low power consumption, the same thing here also we are looking at. So as you can see, this effective current that we are, power that we are dissipating is low. Say, when we go with a 40 macroampere excitation, we draw around 350 macrowatt. And then when we go with 100 nanoampere excitation, we draw around 30 macrowatt. So here we try to see if we can even go with sub macrowatt. This was one attempt to see if we can, and then integrate it with another energy harvesting chip, which is done by another PhD scholar. But because there is no time, I'm not talking about that energy harvesting chip. I just talk about the ADC chip. So this is actually a delta sigma ADC. It's a continuous time delta sigma ADC. And we try to cover a wide range, almost up to 10 kilohertz, to cover most of the applications. So if you look at on the left side, for even a biopotential acquisition system, you have similar requirements. You need a low noise amplifier or instrumentation amplifier. You need gain control. That is something definitely is required because there, you know, this gain control is something that we have in the previous chip as the sensitivity arrangement and the current amplitude arrangement. So instead of changing the gain, we change the amplitude of the input. Here, we cannot change the amplitude of the input because it comes from human body. Therefore, we change it by gain of amplifier. And then anti-aliasing filter and then ADC, right? So we can use our ADC as well. So it's not that we cannot use, but this continuous time delta sigma gives a more compact solution as compared to SAR ADC. And that's why we move to continuous time delta sigma instead of SAR ADC. Though I have also another PhD project going on with SAR ADC. So eventually within our group also we look at two different solutions and each one of them has its own pros and cons. But we wanted to be very compact. That's why we went with it. Continuous time delta sigma. Sub macrowatt power. And yeah, one more thing is here another point is if it is used for wearable applications or applications which are used for implantable or even applications which touch the skin anyway, in addition to energy harvesting and energy autonomous feature, we need also to look at that we cannot make these chips to get heated. You know, because medical eventually standards are higher than other standards and therefore requirements are tougher. And resolution of 9 to 10 bits is good enough for this application. And when we use continuous time delta sigma, there is an implicit anti-aliasing, so no external anti-aliasing filter is required. And maximum stable amplitude of the ADC is limited to VDD, right? And this creates a challenge because at the same time, we want to operate it at low VDD because it's not a system which is directly operated by a battery. It's operated by an energy harvesting chip. Okay, so therefore we need to see what to do, right? So what we did is that we actually, to save energy, we went with a fully passive continuous time delta sigma ADC, one with quantizer. So this is the minimal solution one can think of. With a fully passive filter, and then with a simple DAC, one bit, and we converted everything to current. Adding them is done using resistors. So interesting point here is this is very compact. This is what we wanted to achieve. So it's really compact. So now we have also a methodology for the optimization to make sure that what we get is the best with respect to the area, because we want to make it compact, with respect to SNR, because we want to achieve the maximum number of bits which is possible out of this design, and with respect to the power dissipation. Okay, so this is the details of the flow. Again, is given in our paper. This is another PhD project, which is as a part of the PhD project by Lakshmi Shah. So I showed Shahid, then Miraj, the PhD project, and then Lakshmi Shah's PhD project, part of them. So all of them part of PhD project is shown here. So this also is published this year. You can see it in IEEE TCAS1. So the first paper also is IEEE Sensor Journal. Second one was IEEE JSSC, Journal of Solid State. And third one is IEEE Transaction TCAS1. So you can see all these three papers. And in fact, energy harvesting chip is given in another journal, but I'm not covering it. Now, one interesting point first I want to emphasize here, this chip is fabricated in SCL Chandigarh. This is another point. This is what we are proud of it. The reason is because proud of it, in fact, SCL should be proud of, because this is done within India. This is fabricated and tested, and actually measurement results also were quite satisfactory. And chip worked at the first run. That means that their process also is very stable. So this is very good. So a fully indigenous even ASICs can be developed. So this is one thing just to emphasize. Fabrication is done by SCL Chandigarh. And this is the detailed schematic, which is the same thing I showed you before, only here the comparator is highlighted. And as you can see, the DAC is single bit, therefore a simple inverter is used as a DAC. So this is a very simple design. And it is still, because it is compact, it is fully passive, and it has an optimization loop. Eventually optimization, not loop, sorry, flow. So therefore, it has enough novelty to be published in IEEE Transaction. So what I want to say is that all is done here. That's why I really like to see what is done here, rather than to looking at what is done somewhere else. Somewhere else, I mean outside India. Just to see that, and these are all done by PhD scholars. And you know, power consumption now is sub-microwatt, like around 600 nanowatt, which is very important. Supply voltage is 1 volt. We have another design which is less than that, less than 1 volt, and that I will also show here. Okay, and the clock frequency 2.56, and then SNDR, which is achieved, is around 55 to 58 dB, which is good enough for the 9 to 10 bits that we wanted, and area is really low, it's very compact. So here, it's very interesting experiment I want to show you. So we actually power this chip. Of course, here you can see this chip, which is here, it is shown over here, and then enlarged, the modules are enlarged over here on the chip. So this is the test chip. So he has gone with the kind of hierarchical presentation. So test chip is over here. Sorry, let me go back here. Sorry, I was showing the second one. This is the test chip. So this is the actual layout, because not the entire area was dissipated by this design. So design of this system is here, and this is the layout. So this is the way we show the hierarchical view of this system. This is the test board. Okay, so in fact, these now can sit with the other chip in one. See, you know, energy harvesting chip, ADC chip, INA chip. And now these three can sit, and the diagram that I showed you at the beginning. So one interesting experiment we did here is that we actually empower this test chip using another test chip that we had and designed and fabricated. And this test chip was designed by Gaurav. Gaurav actually worked on the energy harvesting, so that we have published in IITB Journal of Emerging and Selected Topics in Power Electronics. That is also 2020. It's a wide input power range, 500 nanowatt to 1 milliwatt, inductive boost converter with maximum power point tracking for RF energy harvesting. So we applied eventually RF signal to the input, and then we got the DC source, the DC output here at the eventually output, and this is the eventually the voltage that we need to be stored here. We've pre-charged it to 800 millivolt, but it is done only once, and then we leave it. And the system automatically continues recharging this voltage and uses it to generate the DC voltage here at the output shown by VL, which is actually the VDD, goes to VDD of the load. You know, this has gone to the VDD of this chip. And Gaurav and Lakshmisha were very excited because we got the results of the two cases. One case when we use Ketli DC source to empower the chip using the supply DC, and one result, which is, this is eventually the famous noise shaping spectrum of delta sigma. But this, the second plot, which is shown with blue, is actually the spectrum of the ADC, which is empowered by the energy harvesting chip. So this was very interesting. And results also are shown here. Like SNDR is less than 1 dB change. It's around 1 dB now. It's around 1 dB. And dynamic range is around 3 dB change. But really it was very, very exciting to see that this can be done. And therefore it's one step further towards making a batteryless system. So this is the second design of the same continuous time delta sigma with some changes, because now we had to change the circuit because we reduced the supply to 300 millivolts. So therefore, this now is really low voltage. And because of that, power consumption reduced to 200 nanowatts. But SNDR and dynamic range are same as before. So this we fabricated in UMC 180 nanometer. And this also is published this year in IEEE transaction on VLSI. So as you can see, we reduced the stack, number of transistors in the stack to be able to handle everything with 300 millivolt supply. And this comparator also is a new comparator designed to be able to operate with 300 millivolt supply. This is a performance comparison across the two designs that we have and fabricated. One is with SCL technology, and the one which is with UMC also is operated at two supply levels, 300 and 400, to show the difference. Clock frequency is same for all, signal bandwidth is same for all, but you can also compare with the reported works. For example, if you look at the supply level, 300 and 400 millivolt, compatible with reported works. Clock frequency is 2 megahertz, which is reasonably, again, within the range reported. Signal bandwidth is pretty high, 10 kilohertz, but it is, again, compatible with some of the reported works. Now, power consumption is low. In fact, it is reasonably towards the low side. It is reasonably well towards the low side as compared to reported works. Area is extremely low, means that area is, in fact, extremely compact. And this has come also, this specs
which are achieved during the, these are of course measurement results, but design was done based on that optimization algorithm that I told you. And if we normalize the area, you can look at the actual normalized area. The reason why I say normalized area, because technologies are different. You can see we have used 180, this is 65. Minimum size of a transistor in 180 is different from 65. This is actually 2 nodes still are in between, 130 and 90. So it's really almost 4 times. And if you normalize, normalized area actually is very low as compared to most of the reported works. And finally, a figure of merit, which brings several parameters together, which is the bandwidth, power, and knob, effective number of bits, is very low in our case, because lower is better. And you can see this figure of merit is well below all reported works. So conclusion here is 2 eventually continuous time delta sigma designs were reported. One is for minimum 300 millivolt and one is for minimum 1 volt supply. Application operation with energy harvesting system is reported. Also, power consumption is sub microwatt. So we reached to 200 nanowatt around using 300 millivolt supply. Energy efficiency is extremely low, that figure of merit that I told you, almost 25 femtojoule per conversion. Resolution is 9-bit. And if we increase the supply, we can get higher resolution because SNR improves as we increase the supply. Dynamic range at 300 millivolt supply is better than 58 dB, which is good. At 1 volt also was around that time, this value. And design is extremely compact. So less than 0.05 mm square. Okay, I don't think I will have time to go to the next project because that also takes its own time. But if you have, let's see, if you have any question, at least I can just scroll through the next project. Sorry, I told you 3 projects. Actually, there are 4 projects. Any question?
One question is there in chat box. So are simulations carried out before fabrication? Which tools are used?
Yes, for both projects, continuous time delta sigma 2 chips, and then Mera chip, which was the entire chopping, bridge excitation, and INA. All of them were designed in analog design environment, Cadence. All simulations were performed using Spectre. Layout was, and the schematic were done using a Virtuoso toolset. But the final layout verification and, not verification actually, post-layout simulations and extraction were achieved using Calibre from Mentor Graphics. There is one more question. You may tell me because I'm in full screen mode. Yes. I can see the chat box.
So the question is, why only flicker noise is considered and not white noise?
Yes.
Is it because signals are of low frequency?
Yes, that's a good question. Yes. See, signals are of low frequency, therefore flicker noise matters a lot. Flicker noise matters. And flicker noise density, power spectral density at low frequency is much, much higher than the thermal noise. So that is the reason flicker noise was the main bottleneck of the design with respect to noise, not thermal noise. That's the main reason, yes.
One more question is there. Transistors are in sub-threshold mode, something is asked.
Yes, in 300 millivolt design, yes, they are in sub-threshold, yes. You are talking about continuous time delta sigma?
Yes.
Which chip are you talking about? I have shown 3 chips till now. You may mention which one.
Yes, Rathod sir, can you unmute?
Madam, last one.
Last one, yes. In 300, 400 millivolt transistors are operating in sub-threshold. Yes.
Madam, all of these chips are fabricated at Chandigarh? Yes.
No, no, no. These are the UMC. The one chip is fabricated in Chandigarh. This chip. 1 volt continuous time delta sigma is fabricated in Chandigarh.
Yes.
So out of 3 chips I showed you, 1 chip. In fact, we have 1 more chip, but I think in that system, I'm not showing the chip. I am showing only the system. But yeah, out of the 3 chips till now, 1 chip is fabricated in Chandigarh, other 2 by UMC,
Okay. So in one more question is there. In continuous time delta sigma mode, R and C all are in on chip.
Yes, they are all on chip. Yes.
Okay. Why novel MOSFET are not used in analog application?
What do you mean from novel MOSFETs? See, we don't have the opportunity to change the device, right? This is the technology that is given to us, means available for us. What kind of novel MOSFET? You mean FinFET?
Graphene based. She's asking regarding graphene based.
See, what I am presenting right now is the making a full system using the mainstream technologies. Graphene doesn't have any mainstream technology right now. It's all in labs only. It's only research. You don't have any commercial fab for graphene. We need commercial fab, right? Because if we want, because many of these works that I'm showing you, I have also the plan for translational research. So, you know, if you want to commercialize or at least give this available for anybody who want to license it, and you know, these are the plans that eventually institute also would like, and even funding agencies. Towards the end of my talk, I will talk about it. So we need to use a commercial fab, right? There is no commercial fab for graphene, as per my knowledge. For research purpose, anybody can make something, but it's only fabrication. It doesn't go beyond that.
Yes. Any other questions from participant side? Yes. Yeah, done, ma'am.
Okay. So then I will continue. Another dimension. Again, here accuracy matters. What is the topic? To have a gravimetric MEMS-based ultra-fine particulate measurement system. This was for eventually air pollution monitoring, but for ultra-fine particulates, less than 100 nanometers. This is very important. So this is a joint project with Cambridge University, but the entire system and circuit is taken care by us. And the MEMS was designed by them. And of course, MEMS also was fabricated using a MEMS fab. You know, a commercial fab. The way that we send, for example, to UMC, they send to another fab. So now see how it's about this project, because this is like a system level project, but it gives you accuracy. And then see how we can again make systems which can give you the results which are better than available systems, because if you want to use available systems, they are bulky. And if you want to use bulky systems, so everything will be limited to a lab. Or if you want to put them outside, so they become very bulky. So this gives you a compact solution. And we take advantage of here, actually the idea I had was to use a kind of combination of system software. And then see that how we can use system, algorithm, and software to eventually enhance the resolution and accuracy of system. So the whole idea here is you have a resonator. Means that you have a MEMS, which these nanoparticles will be deposited on that. And then there is an oscillator. And then according to that, we will have the complete operation, which is eventually frequency of the oscillator, which has to be measured. So the entire operation relies on this oscillator and measurement of frequency of this oscillator. How accurately we can measure that defines the accuracy of measurement, because as mass of the MEMS changes, the frequency changes. So, but this is, as you can feel, this has to be extremely accurate because we're talking about diameter of less than 100 nanometer. And this is really a very small change in the frequency. So gravimetric MEMS resonators also have different modes of operation. And these modes changes. Sometimes some modes are more sensitive and some modes are less sensitive. That's why it's also important to excite that particular mode to be able to get the results. So this part was mainly the work of the collaborator. And in our case, I focus on the system design. But these are some of the requirements or spec, target spec. For example, we wanted to make a stable system with a measurement accuracy of better than 1 ppm. So we use this as a target, delta F by F measurement. We had delta R by R measurement. Here is delta F by F. And this resonator, frequency may even, you may change the MEMS resonator. So therefore, we designed it for a wide range, from 1 megahertz to 10 megahertz range. And then we wanted to eventually have a dynamic range. Dynamic range is defined with respect to delta F, so as high as 100 kilohertz. And then our project as a part of a PhD, so this is the second eventually project that Lakshmisha did as a part of his PhD. He designed those delta sigma ADCs, and he designed also this system with the help of Adarsh, who was the MTech student and worked with him. So dynamic range of 10 kilohertz with this delta F of 1 ppm gives you resolution of better than 20 bits. It's really tough to achieve. So we made eventually a frequency to digital converter, which is shown over here, high resolution FDC. So this is what the project eventually. And most of the reported FDCs report up to 14 bits, and dynamic range also is very limited. We are looking at 100 kilohertz dynamic. This was a very interesting project. And then the system that we have made, we called it PM2S, particulate mass measurement system. Later on, we made it more specific. We made it Pro-FMS because it's programmable frequency measurement system, which can be used for various applications. So it's not limited only to this application. And this is made using the COTS elements, eventually available systems. So this is published again this year in IEEE Transaction and Instrumentation and Measurement. So Ajay also, who is a PhD scholar, he contributed to the algorithm part, the part that I wanted somebody really to explore and then get the frequency extraction. So I'll talk about it a little. So we used ADC, we had a FIFO, and then a very low power microcontroller, and then clock generator, and then with a Bluetooth system. And here is the other side of the system, which is algorithm. So eventually what we do, we don't measure the frequency, we actually estimate the frequency. There is a difference between these two. Estimation of frequency means that how we can extract the frequency from samples. So therefore, the idea I gave to Lakshmisha day one was, don't do anything with hardware, you just get the samples and move to digital world, and let's see what we can do in digital world. And the reason is because frequency extraction is not so straightforward. You have jitter. When you are looking at delta F by F of 1 ppm, you can imagine how jitter can be problematic, right? So it's not straightforward. So what we have in hardware is Nyquist sampling, a coarse ADC, like it's not a 20-bit ADC. But what we have actually in algorithm and software side, high resolution frequency estimation algorithm. And this PM square is, sorry, square is missing, MEMS, oscillator, and pro-FMS. So therefore, we divide the system this way. So pro-FMS is eventually this part plus algorithm. This is what we call it. And the whole system is PM square S, which is MEMS, oscillator, and pro-FMS. So this also defined work. So MEMS is Cambridge, oscillator, and pro-FMS is IITB. So this way we were able to start working. And of course, we had interactions. It's not like that it's a wall. We had inputs from our side on the MEMS side, inputs from them on the oscillator and pro-FMS, even on the algorithm. So it was a very nice collaborative work. So now this system is a very small system relatively, and you can't imagine this system can easily work that way. So like it's an ADC of 12-bit only. Okay, so then what we used for MEMS, it had a resonator mode of around 3.13 megahertz, and with a Q of almost 2,400. So microcontroller also is MSP controller, very low power. We had an onboard memory FIFO with a depth of 64K. And system operates at 3.3 volt supply. So these are some of the information about the frequency estimation algorithms. You can find them in the appendix of the paper that we have published. So there are various methods, time domain and frequency domain-based frequency estimation. And there is a third angle to that, which happened during lockdown. So during lockdown, Lakshmisha looked at the compressed sensing also, and how we can actually use compressed sensing for frequency estimation. We published that also this year itself, which was one of the work he did during lockdown, because we were not able to use lab at that time. And then that also is published in IEEE Transaction on Circuit and System 1 this year itself. So there you can get more information about compressed sensing part. So these algorithms eventually work in this way. Either you can be in the time domain or you can be in the frequency domain. So like, when you are in frequency domain, you deal with FFT. When you are in time domain, you deal with the samples of the sign. Let's assume this is the signal you receive. Now you want to use these samples to estimate the frequency. Now there are many reported works for estimating frequency from samples. And these algorithms, I don't get into the details of them. For example, Prony's method, which is like, uses these moving samples and then it measures eventually or estimates the frequency from samples in a moving manner using 3 consecutive samples. And what we do is that I told you, we have to assume that we have noise, because these algorithms assume there is no noise. But in our work, we had noise. Therefore, we have eventually worked on this algorithm and then shaped them with the noise in such a way that in the presence of noise, we are able still to extract the frequency. So here I want to show you one example. So look at this frequency measure. This is for 8 megahertz quartz crystal that we used for the eventually one of the algorithms, Kandan algorithm. So look at this frequency which is estimated, right? And look at this value of the delta F by F across these frequencies. So this shows you it can even go below 1 ppm. In fact, we went below 1 ppm. But you may say that, okay, so how do we benchmark? Actually, we used AGLent counter for benchmarking. Of course, AGLent counter also goes up to 12 digits, and we compare, okay? And there are 2 comparisons over here. One is with 64K sample points and one is with 8K sample points, which is faster. Because if you increase number of sample points, measurement time increases. And we use root mean square error as the measure, like figure of merit. And in fact, what we achieve is even better than 0.1 ppm because our collaborator was pushing, let's move to PPP. That's why we moved to 0.1 ppm as a target as project moved on. So yeah, this is that, of course, compressed sensing also is included, the paper here. So these are the results of second table. So two techniques are used, Kandan and Djukanovic, but these are actually results with different type of elements and compared with Agilent counter. For example, 4 megahertz crystal as a reference. So, and in ppm, RMSC in ppm. So this number you see is the error using two different estimation methods. Then for 8 megahertz, these numbers are pretty low. These are below 1 ppm, 0.1 ppm. Then we have MEMS, and there are two modes eventually, SE mode and BF mode, butterfly mode and single mode. So, but here, of course, error increases because see, this is MEMS and this is a crystal, quartz crystal. Quartz crystal is very stable and extremely high Q as compared to a MEMS resonator, but still here is better than 1 ppm. And then if you reduce the time and go with a compressed sensing, which is very nice experiment, and in the compressed sensing, we reduce the accuracy of the ADC to 8 bit. So you can see still with three different estimation techniques and comparison with Agilent counter, we are able to achieve better accuracy compared to Agilent counter. And this is faster measurement. So this is the setup which actually set in Cambridge, but what we did is that this board was carried, Lakshmishwar carried it there, and then there with a collaborator, Professor Ashwin and his student, PhD scholar Mala, they set up in the lab and other collaborators. They set up the lab. In the lab, they've made the setup with actually with silver particle deposition on the MEMS. And then there were two systems. One was eventually a particle counter, which is here, data logger. Then it was our system, ProFMS, which was communicating through USB or Bluetooth with a laptop. And then a frequency counter. So all together, and then this is eventually a photo of the MEMS resonator before deposition, after slow deposition of silver nanoparticles for 50 minutes, and finally with a deposition for 10 minutes, which is accelerated, means that the rate of deposition is high. You can see it's almost like black, because this was for pollution measurement. This is air pollution measurement. You can imagine, sometimes I think our lungs also are something like that. We can clean everything else, but we cannot clean our lungs. This is something really sad. Okay, so these are the experiments which are performed practically. The experiment is as a function of time, because as particle is deposited, the frequency is estimated, change in the frequency. So the circles show the ProFMS, our system, and diamond shows Agilent counter. And you can see very nice matching of the two. In fact, our measurements are showing less variation compared to Agilent counter. And this variation depends on how the resonator is responding with respect to the deposition of particle as time passes. So similarly, delta F by F is shown. This is frequency and this is actual delta F by F. So at the beginning, there is no deposition, delta F by F is 0. So we are at the center frequency. Then the delta F by F starts increasing and reaches almost to at least till 50 minutes, because measurement was done only till 50 minutes, reaches to minus 20 ppm, delta F. And this is the mass collected, because this is that CPC system. So this is the way, like it is 52 picogram per minute, 32 picogram per minute, and then 16 picogram per minute. So this is with respect to arrangement of the deposition. In fact, 16 picogram per minute, this is the value which was the minimum value and gives the highest sensitivity. So which gives us around 0.65 Hertz variation out of 3 megahertz, which is corresponding to around 0.2 ppm per minute variation. This is the slope. Okay, and there is also a slow deposition with silver nanoparticles, very slow, and that's why the variations are not shown, and then accelerated. So they are plotted in the same plot, that's why for slow you don't see the variations. Variations are actually on the left side, which are enlarged. They are around 3.1. Here it goes all the way from around 3.1 down to 3.02 megahertz. So this is eventually, and total deposition is very interesting. At the end of the experiment is around 2,500 nanogram. So 2.5 macrogram. So this, to summarize, this PM square is the entire system and pro FMS our part contribution. We have been able to report 0.1 ppm RMSE, which means SNR of better than 120 dB for the particles with diameter less than 100 nanometer. Dynamic range is very high. Operation is tunable, adjustable. Large range can be adjusted. And then we have also various algorithms which can be chosen depending on the resolution we need and the computation time we can have. It has been demonstrated under lab conditions with respect to the silver nanoparticle deposition with reported sensitivity of 16 picogram per minute and the total deposited value of around 2.5 macrogram particles over time, close to 1 hour. And this is the summary of all these 5 works that I presented to you. And this is something that really I mean, we are proud of all the PhD scholars with their kind of effort, passion, and interest. And all these PhD scholars are going for postdoc from 2021. All already have offers. And I'm happy that their journey, which started around 6 years ago, around 6 years ago, so has resulted to tangible outcomes, not only for the projects, but also for their career and future. And of course, there are many interesting aspects to be followed. But one thing I just want to emphasize is that really all of them worked with passion and not 9 to 5, but actually 24 hours. And without that, it is not possible. And they are being very prompt, being very patient, being very open-minded and giving ideas, accepting ideas. Sometimes we argue, finally, one idea wins, but that is all good and it's fine. So all these systems have many still paths to move forward. So eventually moving towards fully impedance measurement systems, everything auto-configurable, making auto-configurable high resolution, compatible with various types of sensors with wide dynamic range. This is still, a lot of things are left. And we want always to keep these systems to be fully automated with respect to the calibration and calibrate for all non-idealities by themselves, completely self-power. And this itself has a long way to go. So there are a lot of other aspects of this energy harvesting which are still continuing, and I will continue. And eventually moving towards the development and installation of this nanoparticle, because right now the existing systems use laser and they are macro, right? So they are not going to nano, but studies have shown that these ultrafine particulates which settle in long term can result in various types of lung affected diseases. And with today's COVID-19 scenario, we understand that how the health of lung matters. Because health of lung helps to have better, fight of the body with the COVID-19. So I would like to acknowledge, and that is where I want to say that they are interested in IP development modules which can be used by industry, licensing to industry. And this comes from DST, METI, and MHRD. So these projects are eventually sponsored by all these three government agencies, and we are thankful to them. We have a VLSI lab in our department where we design the ASICs, and we have embedded system lab we're testing, and integrated system lab, 2 labs for testing the ICs. And yeah, so that is related to one of the questions that you asked. So it's very important to use commercial fabs to be able to move to the next part, which is licensing to industry. And of course, we acknowledge SCL. It's really fantastic to get chips fabricated by them. And these are the collaborators that I have under these programs from Cambridge and US. And so this is Shahid, this is Laxmisha, and this is Miraj. So, and they were the people who came to the campus back very early stage. And they started pushing, we want to come back to the campus. And 3 MTech students who also did a very good job, Adarsh. He also got the award for the best MTech project and also excellent in academic in MTech program in 2020 in the department. He is currently with TI. Ajay is a PhD scholar who contributed to the algorithms. And Surya also graduated in 2020. He actually designed the chip and he sent it for fabrication. And he also tested the chip and he also demonstrated the board before his graduation. And he's also with TI. In fact, he comes to the campus for recruitment now from last 2 years. So, sorry, Surya didn't graduate in 2020. It's my mistake. Surya graduated 2 years ago, 2018. It's my mistake. I'll correct it. And thank you. Thank you for participating in this training. And I hope I have given you a kind of, transferring the confidence to you that a lot can be done with projects, but you need to keep something in mind that we need to be available at any time, anywhere for anything which comes out of the challenges of the project. If we enjoy doing that, a lot can be achieved. Okay, I don't have anything else. I was not sure if I can make it, but fortunately I could make it.
Thank you, ma'am. Any question from participant sides? I think there are no questions, ma'am. Okay. So actually, ma'am, being my mentor, I know she is very much busy from last 2 weeks. So I really want to thank you, ma'am, for taking time from busy schedule and sharing thoughts on projects developing.
Yeah, thank you. Yeah, Priya, you know that because we had the NSEM exams last week.
Yes, yes.
And I conducted the exam in 2 sessions so that the students will have less time. So connectivity will not be a problem. So that's why it was really hectic. Plus many other things. Priya knows that. Priya knows that. And even today, just half an hour was like a kind of, and continuously emails coming, and then I have to respond. I have to give calls, this one, that one, and you can imagine how much work it takes. But yeah, thank you for also waiting for 5 minutes for me to join. But yeah, that's okay.
Actually, this session has given a lot of exposure to recent projects with the published work, and so that participants will get advantage from it. And I'm sure that your session will benefit a lot of participants present here, ma'am. So, ma'am, I want to specifically tell that we also have a session by Miraj Ahmed. So he is going to tell some basic simulations.
Very
So,
good, very good.
yeah.
When is it? Today?
No, I think it's on Thursday, I think so.
Thursday, okay.
So Miraj Ahmed, actually for participants, I want to tell that Miraj Ahmed is doing PhD under the guidance of ma'am, and we have seen the papers published under ma'am. So you can ask
Yeah,
the
in fact, Miraj is the Miraj PhD is the same chip I presented to you as multi-channel, that resistive sensor with less sensitivity to parasitic capacitors with a dual frequency chopping and INA, on chip INA. So that's the chip Miraj has designed.
Yes, so he is going to give the simulations with some guidance tools. So he's going to show many things.
Okay, good.
Yeah.
Good.
Okay, thank you, ma'am. From on organizing committee, I want to thank you for accepting invitation and gracing this occasion with your presence. So
Thank you.
please
Priya.
accept a virtual memento as a token of gratitude.
Okay, thank you. Should I download it or will you send it to me?
We will send you, ma'am. We will send you, ma'am.
Okay, thank you.
Madam,
Thanks
within 1 minute you will get meeting, ma'am.
Sorry?
Within a minute you will get it. Thank you.
Thank you. Yeah. Now everything is super fast. Thanks.
Yeah.
Thank you.
Thank you, ma'am. Thank you very much. Thank you.
Yeah,
Thank you very
welcome.
much.
So when should I join? 1:15? When is my next talk?
No, it was actually 2 talks were there. Actually, it was up to 150.
Now, it was now only, ma'am.
Oh no,
Oh.
what to do? Yes. What do
It
you
was
think?
now only. So
Okay,
if you
so-
have, madam, if any point of time, if you have, you can tell. We wanted to learn switch capacitors from you, basically.
Okay,
That was
then
the
maybe then what we can do is that we can arrange it on some other day. Is it okay? Or do you want?
Yeah, but when I don't know when you
I don't know.
when you will be free, ma'am, just like that. Afternoon, any day between 2 to 4 will be okay for you. Something like
This
after
week?
2-3 days.
Okay. So this week, right?
Yeah, this week. Course is this week, ma'am.
This week, 2 to 4.
Let me check. May I check now?
Yeah, please.
Yes. You check your calendar, ma'am. Let us know then.
Sure, I'm just checking. So when you say afternoon, what time?
2 to 4.
Madam, actually, in between 2 to 4. Madam, 4th or 5th you check, please.
No, 4th I cannot because we have a full day project review meeting.
Okay.
4th, see, the problem here is we have PhD admissions on 3rd, 4th, and 5th. 4th, I have also a full day project review meeting that I cannot even help in PhD admissions. Then we have only tomorrow and Wednesday.
No, ma'am.
What
Tomorrow is
about-
complete
what
packed
about-
day. Thursday is okay. If Thursday you can.
Thursday we have PhD admissions.
Thursday you can.
3 days, 3, 4, yeah. And because I am also, helping, so I have to keep my time slot open. And because 4th we have a project review meeting, we have also an internal project review meeting on Thursday, starting from 2:30.
Evening time tomorrow evening will be okay to you? 5, 6, like that? 5 o'clock.
Tomorrow evening, 5 to 6. Yes, I can make.
Tomorrow
5 to 6 tomorrow?
Yeah, tomorrow evening 5 to 6.
Should I book it? Should I mark it in my calendar?
Yeah. Participants is okay now for you. Extra you'll have to. I think it's okay.
Is it okay?
Yeah, ma'am. 5 to 6 tomorrow evening.
Okay.
5 to 6.
5 to 6.
Ma'am, it's on basics principles of switch capacitor circuits.
Sure. I will eventually use some of the content of the course that I teach in IIT. So I will use the same content and try to And we can make it fully interactive because this is more a kind of teaching rather than giving a talk, right?
Yeah,
So participants can ask detailed questions. So, but it is 1 hour. So I will try to cover, and then of course I will be open also for questions.
Yeah, ma'am. We start at 5 o'clock. It's up to you. We'll start
Okay, fine, fine. I'll mark my calendar. Okay. In fact, I made it till 6:30 in case, for example, you know, for any reason it goes beyond 6. But anyway, but main preparation will be for 1 hour.
Okay, ma'am.
Yeah. Okay. Okay. Fine.
Okay. Thank you.
Okay.
Thank you, ma'am. Thank you
Yeah.
very much.
Thank you. Thanks. Thank you all for listening to me and spending your time. Okay. Okay. Bye.
Okay, ma'am. Bye.
Bye. Hello.
Okay, so participants, today we will meet at 5 o'clock. Dr. Ramesh will be with us. And now you have heard our discussion. So please be ready for tomorrow and day after tomorrow to complete the 2 days marathon. Okay. Thank you very much. We'll meet today evening 5 p.m. So I'll close this meeting.